the enormity of the universe, a concept almost incomprehensible to humans, showcases our limited understanding of our little planet. Deciphering the massive cycles above us helps us realize that we are part of a structure far beyond our solar system and the 200 billion stars within our galaxy. We can see our local galactic neighborhood from our little rock from a grandstand view, though hundreds more stars illuminate the night sky every night as the sun disappears from view. The sun is the star closest to us, 150 million kilometers, 93 million miles. Seen with the unaided eye in the best places on Earth, our galaxy boasts up to 10,000 stars. A galaxy is a large assembly of stars, gas, and dust kept together by gravity. Acting out the life cycles of our universe on a large scale, it offers stars a habitat. Millions of stars abound in the observable universe among roughly 100 billion galaxies. The smallest are dwarf galaxies, with perhaps just 10 million stars. Giants, the largest galaxies, have roughly 100 trillion stars. Most of us nowadays agree that galaxies contain far more stuff than what our telescopes can detect. Believed to surround them are massive halos of dark matter, a mysterious substance undetectable to the human eye, verified by its gravitational pull on visible matter. Still, the gravitational pull of dark matter shapes contemporary galaxy behavior and most likely helped form the early universe. Still, the gravitational pull of dark matter shapes contemporary galaxy behavior and most likely helped to form the early universe. Dark matter, according to scientists, makes up about 95% of the mass in galaxies, including the Milky Way. Dark matter is less interesting, even though it is unlikely to develop into complex, beautiful structures like stars, planets, and humans. This makes the luminous stars, planets, gas, and dust incidental. One of the main problems confronting modern physics is determining the type of dark matter. We will re-examine the intriguing subject of dark matter later in the book. Galaxy comes from the Greek Milky Circle Galaxy name. Though they first used it to characterize the galaxy that rules our night sky, the Greeks first needed to understand its scope. Although seeing the center of our galaxy emerge in the night sky is a wonderful natural display, sadly, the glow from our cities has deprived us of this amazing nighttime performance. Many people confuse the hazy band of light for storm clouds rising from the horizon, but billions of stars become apparent as Earth rotates towards the galactic center, stretching thousands of light years inward. Greek mythology holds that Hera, Zeus's wife, spilled milk, creating a thin band across the night sky that reveals this ethereal light. The Milky Way, the name we use now for our galaxy, sprang from this story. The Milky Way galaxy boasts 400 billion stars overall, depending on the concentration of rare, faint dwarf stars. Most a disk with an average thickness of 1,000 light-years and a diameter of 100,000 light-years contains the majority of stars. It is extremely challenging to imagine such vast distances. 1 light-year is the distance light covers in a year, roughly 9.5 trillion kilometers, 5.9 trillion miles. Traveling across our galaxy at a distance of 100,000 light-years, light moving at 300,000 kilometers, 186,000 miles per second, would take 100,000 years. Stated differently, the distance separating the Sun from Neptune, the outermost planet in our solar system, is believed to be the center of every galaxy, including our own. Supermassive black-we measure the distance in light hours, equivalent to 1/6 of a light day across all galaxies, including our own. The distance is measured in light hours, which is equivalent to 1/6 of a light day. You must line up about 220 million side-by-side solar systems to cross our galaxy. We believe that supermassive stars center in every galaxy, including our own. Accurate observations of the orbit of the star S2 support this idea. These observations lead astronomers to believe that Sagittarius A, which is also sometimes called the Sagittarius A star and is a strong radio source at the center of the galaxy, is the center of this. With an orbital period somewhat longer than 15 years and speeds up to 2% of the speed of light, S2 is the fastest orbiting object presently known to exist, We can ascertain an object's mass from its precise orbital path. Sagittarius A has a mass 4.1 million times that of our Sun. Given that the star S2 approaches the object at just 17 light hours, Sagittarius A must be smaller than this. This should not be the case. S2 would run across it directly. Astronomers are sure that a massive black hole resides at the center of the Milky Way, since there is no other known way to fit 4.1 million times the mass of the Sun into a region less than 17 light hours across. To validate and enhance these results, recent studies have looked at another 27 stars, known as the S stars, that circle very near Sagittarius A. Archer's cluster is the densest known star cluster in the galaxy. Smaller than our Sun, these stars are made of roughly 150 young, very hot stars that burn brilliantly and have a limited lifetime. They run out of hydrogen in millions of years. Beloved among the stars of our galaxy, the Pistil star lives in the quintuplet cluster and is thought to be nearing death, ready to burst as a supernova. The highest star densities are star clusters in the center of our galaxy, such as the Arches and the quintuplet. As one moves farther from the densely inhabited galactic center until they reach the galactic halo, a sparse cloud of gas in the Milky Way's outermost regions, the number of stars falls. The Sun and Neptune, the furthest planet in our solar system, are separated by 1/6 of a light day, or about 4 light hours. To span our galaxy, you must line up 220 million solar systems. In 2007, astronomers at the Paranal Observatory in Chile tracked the oldest Milky Way star using the Very Large Telescope, VLT. Approaching the end of its life, the red giant star HE 1523-09001 is a massive construction bigger than our Sun, but has a far colder surface. 5 radioactive elements, uranium, thorium, europium, osmium, and iridium, have exact concentrations measured by astronomers in HE 1523-09001. This makes the star fascinating. Astronomers have found the precise age of this ancient star by applying a technique like carbon dating, which archaeologists use to ascertain the age of organic material on Earth. Radio dating is a reliable and accurate technique when several radioactive clocks are running concurrently. Finding 5 radioactive elements in the HE 1523-09001 light was vital. Nearly as old as the universe, which started somewhat over 13.7 billion years ago, this dying star has an age of 13.2 billion years. This star would have produced the radioactive elements created by the first generation of stars, which ended their lives in supernova explosions in the first 500 million years of the universe. 4 spiral arms comprise our barred spiral galaxy: Perseus, Norma, Scutum Centaurus, and Carina Sagittarius. A disk of gas, dust, and stars surrounds a bar-shaped core from which each spiral arm extends outward. Perseus, Norma, Scutum Centaurus, and Carina Sagittarius. The Orion spur, an outgrowth of the latter, houses our Sun. Recent research, however, suggests Norma may have an extra arm with branching off behavior. Our arm here is the outer arm. Near the inner edge of the Orion spur, the star most famously known in our galaxy is the Sun, now regarded as an average star even if it shines brighter than 95% of all other Milky Way stars. We call it a main sequence star since hydrogen fusion with helium generates light and energy. Every second, the Sun's 600 million metric tons of hydrogen create a fusion reaction that generates 596 million. The 4 million tons of mass in the Sun's photosphere gradually absorb and release light into the galaxy and the universe. Comprising our Milky Way galaxy, the Andromeda galaxy is our closest galactic neighbor. When we stare out into the Milky Way, the stellar life cycle is evident even though our Sun is in the middle of its life cycle. The Milky Way births a fresh star yearly, and our galaxy gains a new light source. One such star nursery is the massive interstellar cloud of gas and dust known as the Lagoon Nebula, which generates fresh stars. In 1747, the French astronomer Guillaume Le Gentil came upon the Lagoon Nebula, one of our galaxy's few clearly visible, actively star-forming areas. Though gravity causes the massive cloud to progressively collapse, some areas have low density. These regions progressively gather more matter. Finally, these clumps reach enough mass to create stars. At the heart of this vast stellar nursery, an intriguing object named Herschel 36 shines on the hourglass. This star is classified as ZAMS, zero-age main sequence, since most of its energy is generated by hydrogen fusion, which has recently started taking place in its core. Recent observations show Herschel 36 consists of 3 huge young stars orbiting each other. The whole mass of the system exceeds 50 times that of the Sun. Herschel 36 thus is a real system of giants. Every Milky Way star, including Herschel 36, will finally fade away, and many will do so brilliantly. The remains of a stellar explosion in an unstable star system comprise the 2 soaring clouds of gas and dust that define Eta Carinae. The system comprises at least 2 giant stars, shining 4 million times more than our Sun. One among these stars, according to scientists, is a Wolf-Rayet star. These stars are big. Their mass exceeds 20 times that of our Sun. Losing enormous mass to a strong solar wind every second, the Sun always battles to preserve its outer layers. Eta Carinae, one of the most brilliant stars in the universe, exploded in 1843. Originally thought to be a supernova explosion, the explosion was so brilliant that matter was spewed at almost 2.5 million kilometers per hour, 1.5 million miles per hour. Even if Eta Carinae survives and hides inside these clouds, its survival time is only a few days. The enormous mass of the Wolf-Rayet star causes its hydrogen fuel to run out quickly. Though this could happen sooner, scientists estimate the star will explode in a supernova or even a hypernova, the biggest explosion in the known universe, in a few 100,000 years. Over 70 million light-years away from the Milky Way, a galaxy experienced an explosion akin to the Eta Carinae event of 1843 and 2004. 2 years later, the star erupted into a supernova. Just 7,500 light-years distant, Eta Carinae has the potential to shine so brilliantly as a supernova that it could be seen from Earth during the day. Observing the life cycle of the universe and the light emanating from these distant worlds serves as a reminder that light serves as the ultimate messenger, capable of transmitting knowledge about the beauty of the universe across interstellar and intergalactic distances. But light allows us to travel across time, providing a real and direct link to the past, not only allowing us to see far-off worlds. The properties of light, and the knowledge it carries, make this seemingly unachievable state of affairs possible and feasible. Eventually, the stars of the Milky Way will die. Many will explode quite violently. Herschel 36 emerged from an amazing explosion in the Eta Carinae system. A basic question we must ask ourselves to understand the world is the nature of light. It is our primary tool for planet observation and the only way we could ever venture outside our galaxy to tour the universe. Even the stars are far from us. Our knowledge of them comes from their light. Several eminent scientists explored light's characteristics extensively by the 17th century. Concurrent developments in science and engineering provided significant new insights and motivated one another. Driven to study the universe on all levels and produce significant discoveries and advances in fundamental science, Kepler, Galileo, Descartes, and some of the later true physics greats, including Huygens, Hooke, and Newton, sought better lenses for microscopes and telescopes. By the end of the 17th century, two rival, equally valid theories of light had evolved. In his 1675 book, Hypothesis of Light, Sir Isaac Newton suggested that light comprised particles, also known as corpuscles, while his main scientific rival, Robert Hooke, and the Dutch astronomer and physicist Christian Huygens disagreed. Most physicists backed Newton in the continuing particle-wave debate until the dawn of the 19th century. Renowned mathematician Leonhard Euler is one well-known exception. He thought only a wave theory could explain the diffraction events. In 1801, English Dr. Thomas Young published the results of his famous double-slit experiment. The results clearly showed that light diffracted, which meant it had to move in the form of a wave. Clarifying the beautiful and fascinating phenomenon of diffraction without waves is difficult. A complex but regular pattern of light and dark areas is seen when light passes through a barrier with a rather thin slit cut in it. The screen opposite the slit shows no strong light. The justification is that sometimes combining several waves calls for totalizing. Suppose you have two waves stacked on top of one another with the same wavelength and wave height, also known as the amplitude, but are aligned so that the peaks fall precisely on top of one another, producing a 180-degree phase difference. The waves thus cancel one another. Should these waves be light, there would be darkness. Diffraction experiments show this exact phenomenon through small slits. The slits act as several tiny light sources separated somewhat apart from one another. This means that the light and dark areas that Young and other scientists have seen are caused by wavelengths outside the slits, cancelling each other out and adding up. This amply illustrated how the light was a wave, but what sort? As is often the case with science, the right theory for the character of light came from an unanticipated source. In the middle of the 1800s, many outstanding scientists were investigating electricity and magnetism. Michael Faraday pursued his preferred scientific activity, experiments with wire and magnets, at the Royal Institution in London. He found that pushing a magnet through a coil of wire generates an electric current that moves in time with the current. Today, every power plant on Earth is run by this generator, which provides energy access. Faraday had no desire to establish contemporary society's foundation. He wanted to learn about electricity and magnetism. Faraday's law of electromagnetic induction is the mathematical encoding of his experimental data, now known as simultaneously. French mathematician and physicist André-Marie Ampère found a force between two parallel wires carrying electric currents. Today, the unit of electric current is the ampere, or amp, defined by this force. To produce an attractive force of 0.007 newtons between two parallel wires of infinite length and negligible diameter, 1 amp of current has to pass between them. Changing the 13-amp fuse in your plug the next time will help you pay a modest tribute to Ampère. Currently referred to as Ampère's law, this law has a mathematical expression. We understood a tremendous deal about magnetism and electricity by 1860. Electric currents can deflect compass needles in the same manner as they do magnets. Despite the connection between these two events, a comprehensive explanation has yet to emerge. Scottish physicist James Clerk Maxwell made the breakthrough by developing a single theory of electricity and magnetism capable of explaining all of the experimental efforts carried out by Faraday, Ampere, and others in a sequence of papers published in 1861 and 1862. However, Maxwell's greatest achievement in scientific history came in 1864 when he turned out an unmatched paper. Maxwell discovered that combining electrical and magnetic events into a single mathematical theory reveals an amazing prediction later when Albert Einstein referred to Maxwell's 1860 papers as the most profound and fruitful that physics has experienced since the time of Newton. Two fresh concepts, electric and magnetic fields, unite magnetism and electricity. Modern physics revolves around a field. A simple illustration of what a field might depict is room temperature. Taking a temperature reading at every point in the room and recording it would produce an extensive list of figures showing the temperature changes from door to window and floor to ceiling. The temperature field has this range of values. To introduce the concept of a magnetic field, you could similarly hold a compass at several points around a wire carrying an electric current and note how much and in which direction the needle deflects. The magnetic field, shown by the numbers and directions, is Maxwell found he could create a single set of equations covering all known electrical and magnetic phenomena by giving the electric and magnetic fields top priority. Given how abstract this seems, we should streamline it. C is the speed of light. 0 and 0 indicate the strengths of the electric and magnetic fields. The most convincing proof that light is an electromagnetic wave comes from the experimental measurement of its speed on a benchtop, employing wires and magnets. What relevance does this have to the light? Something deep reveals the actual beauty and power of modern physics. Maxwell found that he could rearrange his equations into a more condensed and magically revealing form by using some simple mathematics when recording his laws of electricity and magnetism using fields. Wave equations emerged from the formulation of his new equations. Stated differently, their form was exactly that of the equations explaining the motion of sound waves across the atmosphere or water waves across the ocean. Waves of what Maxwell discovered within the waves of the magnetic and electric field. His formulations showed that changing electric fields produce changing magnetic fields. But a changing magnetic field generates a changing electric field, which generates a changing magnetic field, and so on. Therefore, eliminating the electric charges generating the electric and magnetic fields can still result in their swaying. One field falls and the other rises. This cycle never stops as long as you do nothing. This is a noteworthy ending. Yet another, even more important one exists. Maxwell's equations also forecast the speed with which these waves must flee the electric charges producing them. Maxwell was well aware of, and had measured by, Faraday, Ampere, and others, that the ratio of the electric and magnetic field strengths determines the speed of the waves. Maxwell must have dropped out of his chair working through the arithmetic. As his equations had predicted, he found that the waves in the magnetic and electric fields moved at the speed of light. Maxwell discovered, rather differently, that light is nothing more than electric and magnetic fields sloshing back and forth and pushing each other across space. How wonderful it is that some mathematics and a bit of Scottish genius mixed with the work of Faraday, Ampere, and others using wire coils and bits of magnets could produce such a profound conclusion. In modern terms, we would characterize light as an electromagnetic wave. Maxwell had to know the exact speed of light to make his breakthrough. As we have known for almost 200 years, light moves astonishingly fast, though not indefinitely. Old Rømer first measured light in 1676, as we will see now. When you open your eyes, the entire world opens before you. Light seems to leap from object to retina, instantly painting a picture of the surroundings. Aristotle and many other thinkers and scientists believed energy traveled without movement, since light seems to travel at an infinite speed. Still, how quickly it travels persisted for thousands of years as the Greek philosophers dug further into the nature of light. Prominent thinkers, including Euclid, Kepler, and Descartes, sat in one corner, bolstering Aristotle's belief that light moved at an unbounded speed. Empedocles and Galileo, however, thought that light could only move at a limited, if rather high, speed, despite their almost 2-millennium gap. Empedocles' refined thinking was 1 century ahead of that of Aristotle. As he considered light crossing the vast distance from the sun to Earth, he realized everything that moves needs to go from one place to another. After leaving the sun, the light has to be somewhere between it and the Earth. It must, hence, move at a limited speed. Aristotle disproved this by using his theory that light is just a presence, and not something that moves between objects. We can only decide among these points of view using experimental data. Galileo started intending to use 2 lamps to measure the speed of light. Galileo held 1 lamp while his servant stood a helpful distance away. Galileo removed the lamp's shutter to release the light when they were in position. Galileo opened his shutter in response to seeing it, then tried to note the interval between the moment his assistant's lamp lit the flash. He believed light must travel fast since he could not gauge its speed. Still, Galileo could limit the speed of light by declaring it must be at least 10 times faster than the speed of sound. Galileo could accomplish this since, had he moved more slowly, he could have noted a time delay. Therefore, instead of considering the impossibility of gauging the speed of light as a no result, we considered it evidence that light travels faster than the equipment he used in his experiment. For countless years, scientists have struggled to understand the speed of light. Seeing how light travels from the sun to Earth helped them find some answers. Danish astronomer Ole Rømer, in the 17th century, produced the first experimental data indicating the speed of light was not infinite. Rømer tried in 1676 to solve one of the day's most important scientific and engineering challenges: see time telling. While mechanical clocks depending on pendulums or springs also needed to be more adept at rapidly becoming out of sync and bouncing around on the waves, sailors needed to find an accurate clock to negotiate the oceans. You must know your latitude and longitude to find your precise place on Earth. Determining your latitude in the northern hemisphere requires figuring out the angle of the North Star, Polaris, above the horizon. With enough astronomy knowledge and trigonometry, you can find your latitude even though there isn't a star exactly overhead the South Pole in the southern hemisphere. Safe navigation depends on this information. Your time zone complicates star longitude search. 0 degrees longitude defines Greenwich in London. Your time zone changes when you travel west from Greenwich across the Atlantic, resulting in New York's early-in-the-day difference from London. Moving east from Greenwich alters your time zone. Moscow and Tokyo are thus later than London. The sun's passage across the celestial pole, symbolized by the North Star in the northern hemisphere, and an imaginary arc spanning the heavens between the north and south points on your horizon, determines the exact time zone you are in at any one location on Earth's surface. It is known among astronomers as the meridian arc. Any day, the sun reaches its highest point in the heavens at sunrise in the east and sunset in the west at the meridian. We call it midday or lunch here. The Earth rotates once on its axis every 24 hours, rotating 15 degrees every hour. This means that at noontime, 2 sites on Earth's surface, 15 degrees apart in terms of longitude, will be exactly 1 hour apart. Set a clock to 12 Haun, when the sun reaches Greenwich's zenith, then find your longitude. Your clock shows 2 p.m. The sun is at its zenith 30 degrees west of Greenwich. Tracking time over weeks or months calls for a rather exact clock. Early in the 17th century, King Philip III of Spain promised a prize for creating a precise technique for computing longitude from a far-off site of land. Scientists began looking for highly precise natural clocks, since building sufficiently accurate ones would be technologically impossible, making it logical to look up at the heavens. Galileo was sure he could use the orbit of Jupiter's moons as a clock once he found them, since they regularly passed in and out of the shadow of the big planet. Jupiter has 4 brilliant moons seen from Earth, and Io, the innermost moon, circles the planet exactly once every 1.769 days. The concept is quite simple. Its steady orbit lets you see Io's daily disappearance and re-emergence behind Jupiter's disk. Galileo thus devised an accurate method of time using the Jovian system as a cosmic clock. Galileo's reasoning did not win him the King's Prize, even if seeing the eclipses of these small pinpoints of light from a rolling ship at almost 750 million kilometers, 500 million miles from Earth, was impractical. Even with these problems, it was clear right away that this method could accurately find longitude on land, where conditions were stable and high-quality telescopes were simple to get. Tracking and documenting the eclipses of Jupiter's moons, particularly Io, became thus a major scientific project. In the middle of the 17th century, Giovanni Cassini oversaw the investigation of Jupiter's moons. He first calculated longitude using Io's eclipses and published tables, which included highly accurate time predictions and details on when the eclipses should be seen from different parts of Earth. He sent one of his astronomers, Jean Picard, to the Uraniborg Observatory near Copenhagen to hone his longitude tables. Picard then sought the help of a young Danish astronomer called Ole Rømer. Over a few months in 1671, Rømer and Picard noted the times and intervals between more than 100 eclipses on Io. At the Royal Observatory, Rømer made a major discovery. Cassini immediately sought him to be his assistant. Combining the Uraniborg data with Cassini's observations from Paris let Rømer realize that the celestial accuracy needed for the Jovian clock was greater than hitherto thought. My projected date of departure from behind Jupiter changed over several months. At some times of the year, the actual eclipse timings deviated greatly from the expected times by more than 22 minutes. This rendered Io useless as a clock, and stopped the notion of using it to determine longitude. Rømer gave a deft and accurate account of what was happening. Rømer observed that as the planets circled the Sun and subsequently drifted back again when the distance between Jupiter and Earth started to drop, the observed time of the eclipses drifted later than expected. This resulted from the planet's growing remoteness from the Sun. Rømer was a genius in realizing that the error was independent of Io and only depended on the distance between Earth and Jupiter, suggesting nothing was wrong with Jupiter and Io's clockwork. His justification was simple and accurate. Assume that light moves from Jupiter to Earth within a given period. This time will rise with the planetary distances. This suggests that the longer it takes for the light to reach you, the later I will come out of Jupiter's shadow. Later than expected. Conversely, light travels farther and faster as Jupiter approaches Earth, which causes Io to show sooner than anticipated. The idea makes sense. This idea makes sense when considering the distance light covers from Jupiter to Earth. Through trial and error, Rømer could precisely depict the shifting times of the observed eclipses. Rømer's computation produced a figure for roughly 20-minute light travel time across Earth's orbit around the Sun. Possibly because he thought the size of Earth's orbit was unknown with sufficient accuracy, he never converted this figure into the speed of light in any Earth-based unit of measurement. He claimed that light moves around the orbit of Earth in 22 minutes. Sharing Rømer's measuring, the Dutch astronomer Christiaan Huygens first measured and published the speed of light. Huygens notes a speed in unusual units of 110 million toises per second in his Treatise sur la lumière, 1678. 2 meters, or 7 feet, makes a toise's speed 220,000 meters per second, not too different from the current value. The Earth's orbital radius around the Sun primarily contributes to the error. Although the speed of light was not agreed upon until after Rømer passed away in 1710, his exact interpretation of the Jovian clock's wobbles remains an incredible feat in scientific history. By measuring the speed of light, he was the first to enable scientists to ascertain the value of what we consider a natural constant today. From the Big Bang, these constants, necessary for the features of our universe, Planck's and Newton's gravitational constants, have remained the same. Physics depends on these values. Even a tiny change in them would fundamentally alter the character of life as we know it. Everything in the universe has a speed limit. People seemed obsessed with surpassing it during the 1900s. In the 1940s and 1950s, the sound barrier acquired an almost legendary reputation as engineers all around tried to build aircraft that could exceed the speed of 1236 km/h, 768 mph, in the air at 20 degrees Celsius. What, then, does this speed limit imply? What does it imply, and how does the fundamental physics affect our engineering attempts to break it? Sound in a gas-like environment is a dynamic disturbance of molecules. Think about allowing the lid of a saucepan to drop to the floor. The air beneath rapidly compresses as it falls, and the molecules get closer together. The higher density of air under the lid hence raises air pressure. Winds between high and low pressure areas develop in our atmosphere as molecules in a gas migrate about trying to equalize the pressure. Some molecules from the high pressure area under a falling lid rush into the lower pressure areas surrounding it. These molecules rush into adjacent areas in response to the pressure rise, and the process continues. The lid falling causes a pressure wave to disturb the surrounding air. Only the pressure pulse moves through the air, producing a low-pressure area that calls for equalization instead of the air flowing away from the lid. The pilot rolled the Hawker Hunter, and at 12,800 meters, we plunged upside down through the clouds. We passed practically right away across the sound barrier. The features of the air set the speed of this pressure wave. The temperature of the air, its average molecular speed, the mass of its molecules — air is mostly made up of nitrogen and oxygen — and the details of its compression response, calculated using the adiabatic index, all affect how fast it moves. The average speed of air molecules at a given temperature controls, to a reasonable degree of approximation, the speed of the sound wave. Consequently, there is no reason an object shouldn't surpass the speed of sound, which is only the speed at which a pressure wave passes across the atmosphere instead of a speed limit. Despite the widespread knowledge of this fact prior to the invention of aircraft, those who aspired to exceed the speed of sound were not satisfied. Though many attempted to build one during World War II, Chuck Yeager became the first person to fly a supersonic aircraft on October 14, 1947, shattering the sound barrier and descending from the bomb bay of a modified B-29 bomber. The speed at which a pressure wave passes through the atmosphere defines the speed of sound, not a speed limit. Although modern aircraft often break the sound barrier, this common feature conceals the significant aerodynamic and engineering challenges people must overcome to travel faster than sound. Test pilot Dave Southwood demonstrated these challenges while constructing the magnificent Hawker Hunter, a plane not intended to break the sound barrier during level flight. Designed in the 1950s, the Hawker Hunter is the eminent British jet fighter from the post-war era. Mach 0.94 in level flight is the only reach of this aircraft. Hence, it is non-supersonic. With the right treatment, though, it can break through the sound barrier and reach more than 1,200 kilometers per hour, 745 miles per hour. Rising to 12,800 meters, 42,000 feet, we reversed the Hunter and turned fully toward the Bristol Channel. The jet passed across the sound barrier, altering the airflow and producing an explosive ground sonic boom. The pilot rolled the Hawker Hunter, and at 12,800 meters, we plunged upside down through the clouds. We passed across the sound barrier practically right away. Consequently, the sound barrier is not a barrier at all. It is only a speed limit for sound set by the laws of physics controlling air molecule movement. Does a similar light barrier exist? Our understanding of light as an electromagnetic wave verifies this. Shouldn't strong enough aircraft or spacecraft be able to fly faster than a wave in an electric and magnetic field? The light barrier is unique and unbreakable in theory. The universe regards light speed far more importantly than its travel speed. Thanks to his unique theory of relativity, Albert Einstein at last grasped this speed: 299,492,458 meters, 983,571,503 feet, in 1905. Inspired by Maxwell's work, Einstein created a theory known as space-time, which aggregates space and time into one harmonic whole. With conventional north-south, east-west, and up-down directions, Einstein proposed adding a fourth direction, past-future, to our planet. Time is the fourth dimension. Thus, we call space-time four-dimensional. Maxwell's equations for electricity and magnetism collided with Newton's 200-year-old laws of motion, which drove Einstein to venture down this dangerous path. Einstein combined space and time rather than rejecting the Newtonian ideas of separate entities. Einstein's theory holds that, independent of their respective motions, space-time comprises a single speed that all entities must agree upon. Regardless of their activities, this special speed, a universal constant of nature, will always be 299,792,458 meters, 983,571,503 feet, at all times and in all places throughout the universe. Einstein's theory depends on this, since it helps us to avoid acting peculiarly in space-time. After all, if the past and future point in different directions from the north and south, why can we not migrate back and forth in space-time? Why can we not live in the past, but only in the future? In Einstein's theory of relativity, this universally agreed special speed distinguishes the direction of time from space and forbids time travel. The speed is subtly woven into our universe's structure of space and time. What is the relationship between light speed? The speed of light and light speed have no appreciable relationship. Light moves at this speed for a purpose, not just happenstance. Einstein's theory holds that everything devoid of mass must travel across space at a designated speed. However, objects with more mass must move more slowly. As light particles, photons have no mass, so they move at the speed of light. Light moving at the speed of light cannot exist, since photons must be massless particles, for some reason beyond our knowledge. Measuring the speed of light only allows us to ascertain the particular speed we call light speed. The speed of light, woven into the fabric of space and time, defines one of the universe's fundamental properties. Universes can travel mass-wise at this speed. Nothing can travel faster than this speed. This university has the following characteristics. Time travel into the past is forbidden, and the past is kept safe from the future. Unaware of it, we create the least amount of time travel back in time. Light moves slower than infinite speed. Thus, you see everything as it was in the past. Though irrelevant in daily life, this odd fact has fascinating consequences. Though light travels 30 centimeters or 12 inches in just a millionth of a second, you could have seen your reflection in the mirror before. The delay is hardly noticeable. Conversely, the delay gets more pronounced as object distance grows. Though the influence is always negligible over small distances, sky-gazing and training as an astronomer will have far-reaching results. Looking up at the moon, you see our closest neighbor from long ago. On average, it is 380,000 kilometers, 23, a discernible but minor distance. But if you stare upon the sun, you will sink into the past if you go by cosmic standards rather closely. The sun is 150 million kilometers, 93 million miles. The speed of light seems rather regular at these distances. The sun was here 8 minutes ago. The odd outcome is that we would still be able to feel the sun's heat on our faces and see its image brilliantly shining for 8 minutes in the sky, even if we could magically remove it. This delay also relates to gravity, since the fastest speed of any force in the universe is that of light. We could still see the sun for 8 more minutes and round it, even if magic caused it to disappear. Looking at the sun, we really travel back in time. Still, our time travel excursion is far from done. Analyzing the planets and moons of our solar system lets us travel much further back in time. The time it takes for light from Mars to reach Earth may vary from 4 to 20 minutes depending on the relative positions of Earth and Mars in their orbits around the Sun. This greatly affects the building and running of vehicles on Mars's surface. At Mars's furthest point from Earth, identifying and instructing a Mars rover to stop running across a cliff would take at least 40 minutes, requiring slow operation or autonomous decision-making. Jupiter takes roughly 32 minutes to reach from its closest point to Earth. Neptune, the planet farthest from Earth, takes roughly 4 hours to reach by the time we reach the farthest points of our solar system. Radio signals emitted and received by Voyager 1 on its trip into interstellar space travel 31 hours, 52 minutes, and 22 seconds as of September 2010 to reach their destination at the edge of the solar system. But look beyond our solar system. Light moving from our surrounding stars now takes years rather than hours or days. Alpha Centauri, the closest star to Earth, is seen with the unaided eye as it was 4 years ago. As cosmic distances grow, we travel further back in time. With its luminous arc and a glittering mist of innumerable stars, the Milky Way galaxy rules the sky. All observed light sources and stunning mist patches seen with the unaided human eye come from the 2 small dwarf galaxies orbiting the Milky Way, the Magellanic Clouds, and stars in our own galaxy. There is only one exception to this rule. Locating the Cassiopeia constellation starts with realizing its unique W form. It is across from Polaris, the North Star, and opposite Ursa Major, sometimes known as the Great Bear or the Plough. Being so close to Polaris, Cassiopeia is a constant in the northern sky. At high latitudes, it rotates around the pole once every 20-24 hours and never sets below the horizon. If you mentally line Cassiopeia's V, a large, pale, misty area opens in the sky beneath her W upright. Though not as brilliant as Cassiopeia's stars, it resembles most surrounding stars. Since this meager small patch is a whole galaxy outside the Milky Way, it is the most cognitively amazing object the unaided eye can see. We call our galaxy's closest neighbor Andromeda. It boasts 1 trillion suns, more than twice as many stars in our galaxy. The link is found here, some 25 million kilometers, 15 million miles apart. While our distant relative Homo habilis was foraging on the Tanzanian savanna, a beam of light left the Andromeda galaxy and started to travel across the universe 2.5 million years ago. until one person from that unbroken lineage happened to glance up into the sky beneath the Cassiopeia constellation and focused that light beam onto his retina. Many prehistoric and modern humans lived and died as that light beam traveled through space at the speed of light. Entire species developed and vanished. An electrical signal in a nerve fiber ends 2.5 billion years of travel astounds the human brain, a sophisticated organ not present at the beginning of the road. Examining the night sky with our unaided eyes will only help us so far in our search to unravel the secrets of our universe. Thanks to technological innovations, humanity can access spacecraft and advanced tools that fundamentally alter our view of the universe. With barely 2.5 million light-years separating us from the origins of our species, the farthest point our unaided eyes can see is Andromeda. It was the furthest point back in space, and humans could look without help until recently. With ever more advanced telescopes, though, we can now gaze farther and deeper into space, beyond Andromeda, and retrieve many messengers bearing information from the far past. None have had the same effect on astronomy since Galileo's first telescope as the 11-ton Hubble Space Telescope. During President Jimmy Carter's 1970s administration, Congress approved the Hubble Space Telescope. The original launch date set by President Jimmy Carter was 1983. Problems dogged this ambitious project, named after Edwin Hubble, who found the universe was expanding. A change in the original launch window caused the telescope to be ready for launch in October of 1986, 3 years later than anticipated. However, the Challenger space shuttle's failure, 73 seconds after launch in January 1986, devastated Hubble and the U.S. space program. They paid $6 million monthly for storage fees and kept Hubble in a nitrogen envelope for 4 years. The resurrected shuttle program moved the launch date to April 24, 1990. 7 years later than scheduled, shuttle mission STS-31 sent Hubble into its intended orbit, 600 kilometers, 370 miles above Earth. Hubble's basic appeal was its simple, undistorted deep space pictures, free from Earth's atmosphere. It was clear in a few weeks that Hubble's 2020 vision was far from perfect, but a new perspective was ready to sweep over the immaculate heavens. The returned images amply displayed an optical fault. After preliminary research, the Hubble team progressively concluded that, despite decades of planning and billions of dollars, they had launched the Hubble Space Telescope with a main mirror that was minutely but catastrophically distorted. Hubble's brilliant retina, 2.2 thousandths of a millimeter out of shape, destroyed Hubble's vision of the universe, even if it was supposed to be the most flawless mirror ever built. Given its significance and promise, an ambitious Hubble repair project was soon hatched. Thanks to its design, astronauts could service Hubble in space for the first time. Not able to install a new mirror, NASA engineers found they could fix the issue by arming Hubble with eyewear after precisely calculating the broken mirror's disruptive effect. More than all other telescopes, the Hubble Space Telescope has changed astronomy. As it circles the Earth, this large telescope records images of areas of the universe inaccessible to human view. Since 1990, the telescope has been in orbit around Earth. It is currently working on a novel and revolutionary project. 10 days of new gear in December 1993 let the Shuttle Endeavour crew upgrade the telescope. Astronaut Story Musgrave oversaw the repairs, the most difficult work humans have ever completed in Earth orbit. Musgrave is a living example of what one can achieve when committed to one's objectives. He is a trauma surgeon with 7 graduate degrees, completing 4 shuttle trips and 16,000 hours of test flying in 160 different kinds of aircraft. According to Musgrave, Hubble's sight recovery represented him as a symbol of the space program. Hubble is glorious as a spacecraft or starship. Working on rejuvenation, returning to its former vitality, and returning such a beautiful thing to its roots was a privilege. The effort was major and well worth it. The Hubble Space Telescope's work and possibilities helped me develop a passion. The Hubble Space Telescope has been piecing together these amazing pictures for almost 20 years, enabling us to view events billions of years ago and locations light years away. Traveling to these places will always require assistance. One Hubble picture, though, has done more than any other to portray our universe's vastness, complexity, and beauty. Over 11 days, from September 24, 2003, until January 16, 2004, Hubble captured this image known as the Hubble Ultra Deep Field. During this period, the Advanced Camera for Surveys, ACS, Multi-Object Spectrometer, NICMOS, and Near-Infrared Camera on Hubble were pointed at a small portion of the Fornax constellation in the southern sky. Given the small size of this sky area, Hubble would have needed 50 of these images to completely depict the Moon's surface. Hubble selected it since the small sky area is virtually starless and dark from Earth's vantage point. Hubble's millisecond shutter speed allowed it to record nighttime images of faint, far-off objects. One single photon of light strikes Hubble's camera sensors every minute, creating the image's weakest objects. These luminous specks act as an island of hundreds of billions of stars, almost all the almost 10,000 galaxies seen here. Applying this to the whole sky yields almost 100 billion galaxies in the observable universe, each containing hundreds of billions of suns. Seeing Hubble's masterwork is like a trip beyond human comprehension. The Hubble Ultra Deep Field allows us to traverse the history of the universe. Even more amazing than the image's scale is the sluggish speed of light at the distances of the galaxies. Hubble images are three-dimensional since every one of the millions of galaxies it captured is located at a different distance from Earth. The third dimension, though, is temporal rather than spatial. Hubble's great accomplishments have transported us to a world beyond human reach in past years. The Hubble Ultra Deep Field lets us travel across the history of the universe, much as an ice core exposes layers of Earth's past. The image shows a range of galaxies, some of which differ in age, size, form, and color, and others rather far from us. The closest galaxies have more defined spiral and elliptical forms and are brighter. Having developed shortly following the Big Bang, they are only 1 billion light-years away and around 12 billion years old. Still, the true attraction here is the small, erratic red galaxies. The picture comprises 100 of the most far-off galaxies ever seen. Before they ever reach us, some of these weak red blobs have been radiating light for almost a 13.75 billion-year universe lifetime. Some of these dim red blobs are from more than 12 billion light-years away from us. We discovered the most far-off galaxy in the deep field in October 2010, 600,000 years after the start of the universe. Over 13 billion light-years separate us from it. It is difficult to grasp these huge times and places. Imagine that a few photons of light expelled from burning primordial stars produced the picture of this ancient galaxy. At the beginning of their journey, there was only an embryonic and chaotic mass of young stars and dust before the Milky Way, not Earth nor the Sun. After almost 2/3 of the distance to Hubble's cameras, these tiny light particles emerged from a whirlpool of interstellar dust and dropped into our solar system. The first complex life on Earth emerged almost here, and within a cosmic heartbeat of their ultimate destination, the species that produced Hubble first emerged. Though the Hubble Ultra Deep Field picture reveals a complicated and ancient narrative, how can we draw so much from one picture? Understanding the colors of those far-off, erratic galaxies will help one to find the answer. Among nature's most stunning and well-known beauties are the amazing Victoria Falls. Driven by a powerful river, Zambia and Zimbabwe meet at southern Africa's Zambezi Falls. The falls bear David Livingstone's name, the first European visitor in 1855. "Nobody can imagine the beauty of the view from anything witnessed in England," he said. I found myself exactly in that state. Though European eyes were blind to such exquisite scenery, angels in flight must have seen it. The key to understanding the Hubble Deep Field image is the unearthly quality of the falls, which is equally beautiful and rather more instructive for our purposes. Few sights on Earth have the visceral power of flowing water like this one. A common feature of the Zambian sky is that amazing rainbows linger above the falls as the sun peeks through the mist. For thousands of years, people have been enthralled by rainbows. Seeing one is wondering at a basic but exquisite quality of light. Like most natural events, knowledge of their underlying science improves their beauty. Scientists have tried to understand rainbows by looking for why white light seems to change color since the time of Aristotle. Our old friend Ibn al-Haytham was among the first in the 10th century to try to clarify the physical foundation of a rainbow. According to Ibn al-Haytham, rainbows are produced from sunlight bouncing off clouds before they reach the eye. When Isaac Newton found a glass prism that could split white light into colors, he set the groundwork for our knowledge. All colors, he thought, mix to create white light. The prism and the rainbow arise from the same physical principles. The sun's light combines all colors. As water droplets fall from the heavens, they separate the sunlight into its component hues. Why, though, does a rainbow show a clear arc? René Descartes offered the first scientific justification in 1637, some years before Newton. Descartes considered the possible consequences of one sunlight beam entering a single droplet, since water droplets in the air are basically little spheres of water. The sun's light ray, S, appears below, entering the droplet's face and bending somewhat. When light bends somewhat more at point C, deflects when it emerges from the front once more, reflects back into the raindrop, point B, and passes through a barrier separating two materials, point A. The light ray moves, E, from the raindrop into your view. The light must enter the raindrop and return at D, the maximum angle. Red light, Descartes computed, had a 42-degree angle. Blue light calls for a 40-degree angle. The maximum angles of reflection range from 42 to 40 degrees, for colors falling in the blue-red spectrum. Most light reflects back at this particular maximum angle. Angles outside this produce no light reflection. This offers a reason for the rainbow. Look up at a rainbow and imagine yourself drawing a line from the sun, always behind you, straight through your head and onto the ground before you. At a 42-degree angle to this line, you see the rainbow, or Descartes' red light ray, Descartes' blue light ray, and every rainbow hue falling between can be seen at a 40-degree angle to this line. The sky appears brighter below the arc than above, as shallower angles reflect some light back to your eye. Since all rays mix to produce white light, the colors below the arc are invisible. As the picture on the previous page shows, the sky inside the rainbow is growing brighter, while the sky outside Victoria Falls is rather dark. Raindrops reflect each color component back to your view at a somewhat different maximum angle, separating the white sunlight into a rainbow. But why then the arc, anyway? Rainbows are round in actual terms. Once more, consider the imaginary line separating your head, the Earth, and the Sun. Surrounding the 42-degree angle between this line and the heavens is a circle of points. The arc shows itself when the horizon totally hides the circle. This also clarifies why rainbows appear more often in the late afternoon or early morning. The line separating it from your head slips as the rainbow centered on it approaches the horizon, and finally vanishes behind it as the sun rises. Since Aristotle's time, scientists have sought to understand rainbows and how this media converts white light into color. When the sun peeks through the mist, rainbows appear in the heavens above Victoria Falls, among Earth's most breathtaking views. Radio waves have the longest wavelengths, and gamma rays have the shortest wavelengths in the electromagnetic spectrum. The little range in the middle that our eyes can detect is known as visible light. In reality, rainbows are round, the Magellanic Clouds and stars in our own galaxy. This also explains why rainbows typically appear in the early morning or late afternoon. Descartes established his idea based on the behavior of a single solar light beam entering a water droplet. He found that the colors of light bent or refracted at slightly different angles to one another. In addition to revealing this concealed color in white light, sunshine has additional effects on objects, such as making them bounce or absorb colors in diverse ways. Because blue components of sunlight reflect off air molecules more frequently than other hues, the sky appears blue. The chance of scattering red and yellow light increases as the sun gets closer to the horizon and penetrates more of the atmosphere, making the evening skies redder. Leaves and grass appear green because they reflect the blue and red wavelengths of the sun's green light, essential for photosynthesis. What characteristics of the colors cause them to behave in such disparate ways? The explanation comes from our understanding of light as an electromagnetic wave. The distance between a wave's two peaks or troughs is known as its wavelength. The wavelengths of green and blue light are shorter than those of red and blue light. According to scientific estimates, the human eye can distinguish between around 10 million different colors or 10 million minute variations in the wavelength of electromagnetic waves. One simple idea is all you need to read the Hubble Ultra Deep Field image story. Then, how can we calculate the billions of light-year distances to the asymmetric, disordered galaxies in the Hubble image? The image below shows some of the farthest-reaching galaxies we have seen. The most obvious thing about them is that they're all red. Why is it such a situation? Locating the Cassiopeia constellation starts with realizing its unique To investigate stars known as Cepheid variables, Edwin Hubble employed the most powerful telescope in the world in the 1920s at Mount Wilson Observatory in Pasadena, California. Because the times these stars, brighten and dim, match their inherent brightness, astronomers benefit greatly from these stars, sometimes called Cepheid variables. Their brightness changes every day or every month. In other words, we can easily determine the precise brightness of a Cepheid variable star by tracking its fluctuations over several months. You can calculate something's distance using its perceived brightness. Edwin Hubble's research aimed to identify Cepheid variations in the sky and determine how far away they were from Earth. In the course of his studies, he made two significant findings. Firstly, he quickly deduced that the Cepheid variables he found in the so-called spiral nebulae, formerly thought to be brilliant gas clouds inside the Milky Way, were located far outside our galaxy. Hubble's observations revealed the presence of galaxies that are millions of light-years out in the universe. Science-wise, Hubble's second discovery was even more important. Hubble's group concentrated on determining the light spectrum of stars in spiral nebulae, which are now known to be galaxies outside of the Malay Peninsula. They quickly discovered that many of these galaxies appeared to be producing redder-than-usual light. Redshift is a measurement used by Hubble to determine how much a galaxy has reddened. Since red light has a longer wavelength than blue light, red-shifted sunlight shows that the wavelength is longer than expected, sometimes known as the Great Bear or the Plough. Being so close to Polaris, Cassiopeia is a constant in the northern sky. At high latitudes, it rotates around the pole once every 20. Hubble was amazed to find that his graph was fairly straight. This is because there is a direct relationship between redshift and distance, which means that as a galaxy gets farther away, its light gets stretched or redshifted. Why does this happen? The way that Hubble's result has been interpreted is amazing. Galaxies increase the distance that light has traveled in the universe. Furthermore, as light moves farther, it gets bigger. This association between the distance traveled and the degree of stretching happens when the universe experiences an unanticipated, basic alteration. It's expanding. To put it another way, over the hundreds of millions of years that light has traveled, space has been stretching at a relatively constant rate, extending the wavelength of light directly proportional to the distance it has traveled. As a result of their light having stretched and traveled further across our expanding universe, the galaxies that are the furthest away have the largest redshifts. Our universe is growing due to Hubble's discovery of the so-called cosmological redshift, a significant turning point in science throughout the 20th century. Redshifts were first detected early in the 20th century, and Edwin Hubble's work gave this discovery a cosmic context. He discovered a simple relationship between redshift and galaxy distance. The farther away a galaxy is, the higher its redshift. With increasing distance, light suffers more stretching and travels farther. Hubble's simple graph contains a lot of information. Redshift is the stretching that would occur if anything moved at a specific pace in the distance. The Hubble constant is the gradient of the line on Hubble's graph that shows the relationship between the galaxy's distance and its stated redshift. Its measured value is 68 kilometers per second or 42 miles per second per megaparsec. Astronomers commonly use a megaparsec, or 3.3 million light-years, as a unit of measurement. Based on Hubble's law, a galaxy 3.3 million light-years away from us would regress at about 70 kilometers, 45 miles, each second. That travels a little slowly. The speed of a galaxy 6.6 million light-years away will be regressing, or about 140 kilometers per second, or 90 miles per second. In addition, we can generate a number equal to time units by flipping the Hubble constant. The Hubble constant, 70 kilometers, 45 miles per megaparsec, allows us to determine the universe's age, reaching 14.3 billion years. Form. It is across from Polaris, the North Star, and opposite Ursa Major. An astute reader may have noted, incidentally, that the best estimate of the universe's age that we currently have is marginally less than this, at 13.75 billion years. This is because over the last few decades, accurate measurements have shown that the structure of the universe deviates from strict adherence to Hubble's simple law. The best available data shows that dark energy accelerates the universe's expansion. The universe's significant finding that the universe is the universe was made possible by Hubble's discovery of the cosmic redshift. This could seem challenging, but the outcome is evident and important. The universe's singularity is confirmed by the reddening of distant galaxies. Galaxies must have been closer together in the past. If you continue to travel back in time and observe the galaxies becoming closer together, the inverse of the Hubble constant suggests that they were once stacked on top of each other. Alpha Centauri, the closest star to Earth, is seen with the unaided eye. We commonly refer to it as the Big Bang, which occurred 14 billion years ago. Thus, Hubble's incredible discovery provides direct evidence that the universe had a huge bang about 14 billion years ago. The 1920s deduced this by observing Cepheid variable stars and light from distant galaxies. It is difficult to imagine the Big Bang. It does not seem right to see it as a big empty box, a massive explosion that threw matter into an existing void. The generally acknowledged theory states that space existed before the Big Bang. For clarity, and in the spirit of Einstein, space-time began with the Big Bang. This suggests that the Big Bang didn't just happen in one world, it happened simultaneously everywhere. So the Big Bang happened in your head, in the space between you and this book, on the other side of the Earth, in the solar system, and in distant galaxies. As stated differently, it happened all around the universe. Space existed before the Big Bang, and has only grown larger since then. This leads to the ridiculous conclusion that given its unlimited nature, the universe had an infinite origin. Everything that is here now was here once, albeit incredibly compressed. It was always the intention of cosmology to be complex. As a result, space is expanding, a process that has continued since the Big Bang, and we observe distant galaxies moving away from us rather than because of a massive explosion that happened at the beginning of time. Human eye come from the two small dwarf galaxies orbiting the Milky Way, the Magellanic Clouds, and stars in our own galaxy. There is only one exception. Every second, light from the beginning of time flows down onto the surface of the Earth in an endless torrent. If we could glimpse the light of the universe, it would illuminate the sky day and night. Unaided eyes cannot see the universe. Little fluctuations in the wavelength of the long-wavelength universal glow known as the cosmic microwave background, CMB, suggest that some of this hidden light is not a featureless glow. The cosmic backdrop CMB image, which shows our universe shortly after creation, is one of the most important pieces of evidence in favor of the Big Bang theory of the universe's origin. The Big Bang formed the entire universe in time. There was an infinite cosmos full of stars and galaxies, many of which are still visible today. The universe is still growing, with many new star-forming areas such as NGC 281K and old galaxies. The observable portion of the universe's light is minuscule. Beyond red, the electromagnetic spectrum of the universe extends to wavelengths that are too long for human vision to perceive. Even though we haven't evolved to see it, light is the sloshing back and forth of the electric and magnetic fields pushing across the emptiness at a unique, universal speed. You can feel this light in the Namib Desert by placing your palms against the sand. Long wavelength light causes the dunes to retain heat long after the sun sets. It is referred to by scientists as infrared light, and the single characteristic that sets it apart from visible light is wavelength. Infrared light has a longer wavelength than visible light. We proceed down the spectrum from infrared to microwaves at wavelengths equivalent to a microwave oven. The spectrum then seamlessly crosses into the radio band with very long wavelengths. Throughout human history, we have been blind to these more exotic types of light, but all you need to detect is a radio and high-tech, pricey gear. When you tune a radio, light waves encode information instead of sound waves. Although most radio waves we are accustomed to using for broadcasting and communication are created by people, microwaves and radio waves also naturally occur in the universe. Moreover, microwave and radio photons serve as messengers, just like visible photons from the farthest galaxies, providing our astronomically advanced artificial eyes with exact information about distant locations and times throughout the universe. The Great Bear, or the Plough. Being so close to Polaris, scientists believe about 1% of this is music, strengthened light that has traveled since daybreak. The echo of the Big Bang is audible deep inside the static. We first identified radio waves when we discovered visible light 400,000 years after the Big Bang. The observable universe used to be smaller and hotter than it is now. This order of magnitude is hotter than the core of a star, at 273 million degrees Celsius, a temperature so high that the universe's hydrogen and helium nuclei cannot contain the electrons required to form atoms. The universe was made of exposed atomic nuclei and electrons in a hot ball of plasma temperatures. Light cannot go far in thick plasma, because it bounces off the electrically charged subatomic particles. The light was not free to travel until the universe contracted to the point where electrons could combine with helium and hydrogen nuclei to form atoms. About 400,000 years after the Big Bang, recombination, a stage in the universe's history, occurs at about 3,000 degrees Celsius, a thousandth of what it is now. It is a constant in the northern sky. At high latitudes, it rotates around the pole once every 24 hours and never sets below the horizon. If you time, with its luminous arc and a glittering mist of innumerable stars, the Milky Way galaxy rules Polaris, the North Star, and opposite Ursa Major, sometimes known as the Great Bear or the... But the universe has gotten larger, and light has grown so much that it no longer appears inside the spectrum due to expansion. It has disappeared from the infrared spectrum and is only detectable in the microwave and radio bands. The cosmic microwave background, often known as the CMB, is a long wavelength, weak, universal light that Robert Wilson and Arno Penzias first saw in 1964. This finding demonstrated that every universe had its own beginning. Ignore the state-of-the-art machinery. To locate hidden light sources, all you need is a simple radio. You can adjust it to identify data in a light wave. The visible light of the universe is only a small percentage of it. The infrared image shows the far-reaching electromagnetic spectrum, reaching wavelengths too long for human vision to perceive. It also illustrates the vastness of the universe. Locating the Cassiopeia constellation starts with realizing its unique W form. The Kennedy Space Center in Florida launched the Wilkinson Microwave Anisotropy Probe, or WMAP, on June 30th, 2001. We constructed this extremely specialized telescope to capture the largest known image in the universe of the CMB, on camera. Even though WMAP was retired after 9 years of service, its photo, the most significant sky image ever taken, remains the subject of intense research because it offers rich detail about the expansion and evolution of the intensively studied early universe. A scientist believes this picture is the most beautiful snapshot ever taken, since it contains a plethora of information about the sins of the universe, despite its simplicity and lack of the beauty of a spiral galaxy or nebula. The raw image from WMAP shows the light of our Milky Way galaxy as it creates a blazing bright band across the sky when this detail and other noticeable side effects are removed. All that's left is a straightforward yet meaningful and instructive picture. This night sky image captures the structure of our universe, the recombination period universe, with striking clarity. Throughout its 9-year mission, WMAP has continuously improved the image's detail to show more minuscule details that the early light had previously hidden. We present a sky temperature map using the WMAP data. By measuring the wavelength of the detected light, we may determine the temperature at any given time. Longer wavelengths correspond to lower temperatures, and shorter wavelengths to higher temperatures. The temperature difference between the red and blue sections is only 0.0002 degrees. According to the Kelvin temperature scale, the average temperature of the CMB is 2.725 degrees Celsius above zero, or 2.725 K, or 270.425 C. Despite their tiny size, these temperature discrepancies are extremely significant because they show that certain regions were denser than others in the early universe. These seemingly insignificant differences may not appear significant, but they are vital to survival. This is because the CMB's small blips are the galaxy's seeds. Regions of the universe during the recombination epoch, which were roughly 0.5% denser than their surroundings, are represented by the red patches in the CMB. Because of their increased density, these neighborhoods would have grown more slowly than the university's surrounding districts. Locating the Cassiopeia constellation starts with realizing its unique W form. It is across from Polaris, the North Star, and opposite. These regions would have been 1/5 of their current size, or twice as dense as their surroundings, when the universe originated, a little over 1 billion years after the Big Bang. By now, the stuff in these regions was dense and cool enough to collapse under the force of gravity, creating the first stars and the cores of galaxies, like our own Milky Way. The cosmic period that we view in the most redshifted Hubble Space Telescope data is the development of the earliest galaxies, and the minuscule variations in the cosmic microwave background radiation are the progenitors of these galaxies. The Wilkinson Microwave Anisotropy Probe, WMAP, compiled this thorough picture of the early universe many years ago. The color changes correlate to temperatures that originated 13.7 billion years ago and gave rise to the first galaxies. Denser areas of the institution developed more slowly than other areas due to their higher gravity. When the density of the universe reached double that of its surroundings, the cool, dense matter inside these regions collapsed under gravity to form the cores of the first stars and galaxies, our own galaxy. There is only one exception to this rule. A multitude of suns erupted, their brightness filling the universe with illumination. For billions of years, other universes existed and perished until 9 billion years after the formation of the universe, a star dubbed the Sun universe emerged in the Orion Spur, a common space region found in the Perseus arm of the Milky Way galaxy. This is how the universe's solar system formed in dense space during its phases. However, why do these tiny density changes appear in the CMB? This is the most amazing scientific finding to date. The most widely accepted theory explaining the early universe nowadays is inflation. The theory suggests that the universe underwent a rapid phase, exhibiting a volume rise of approximately 1,078 seconds after the Big Bang. Simplified scientifically, this means an exponential rise in volume occurs just a million millionths of a second after the Big Bang. The entire event transpired within 1032 seconds. Before inflation, the universe's current portion, the hundreds of billions of galaxies that make up our night sky, would have been far less than a single subatomic particle. More than all other telescopes, the Hubble Space Telescope has changed astronomy. As it circles the Earth, before inflation, the denser parts of the cosmic microwave background spectrum are made up of fast expansion, which makes small quantum fluctuations bigger. If the inflationary theory is correct, the cosmic microwave background, CMB, offers a window into an era of the universe's history that precedes the Big Bang. What we are witnessing is etched with the events that transpired in the incredibly incredible first millionths of a second after everything began. I think this is the most amazing idea in all of science. Little creatures like you and me, crawling around on the surface of a rock on the edge of a galaxy, can understand the evolution of the universe and make intelligent conjectures about its evolution by decoding the messages sent to us across the cosmos on beams of light. The constellation starts with realizing its unique W form. It is across from Polaris, the North Star. Science has more amazing stories than any other, and the universe is incredibly beautiful. Its power is actually menacing. There's still a twist in the universe. Light has been our emissary throughout this journey, carrying stories from distant places and the past to our shores. None have had the same effect on astronomy since Galileo's first telescope as the 11-ton Hubble Space Telescope. During President Jimmy Carter's 1970s administration, a recent theory suggests that the development of eyes in animals like trilobites caused the Cambrian explosion. Once eyes have formed, a strong selection mechanism favors the development and improvement of eyes in other predatory species. The Burgess Shale contains a wide variety of trilobite genera. These complex and remarkably preserved fossils have given scientists vital knowledge of the appearance and behavior of these now extinct creatures. That being said, under what conditions did complex life evolve? High in the Canadian Rocky Mountains, these fossil beds contain a hint. The image on the left showcases the sophisticated trilobite, one of the ancient animals discovered here. The most distinctive feature of the now extinct trilobites was their complex, compound eyes, distinguished by their jointed limbs and external skeletons. Because these prehistoric predators could perceive forms, sense movement, and identify them, they could track their prey with their eyes. Due to their ability to see, these trilobites were extremely successful creatures. During the Permian mass extinction, they went extinct 250 million years ago, yet they lived for 250 million years. Our own galaxy. There is only one exception to this rule. Locating the Cassiopeia constellation, natural selection unleashes a new force when a predator develops eyes to aid in its meal hunt. The animals that survive this selection process might evolve more intricate visual disguises to avoid the predators or employ enhanced sensory organs to adjust to this novel threat. Stated differently, once eyeballs have developed, a strong selection mechanism supports their development and improvement in other predatory species. Galaxies orbiting the Milky Way, the Magellanic Clouds, and stars. Similar to an evolutionary arms race, natural selection affects the formation of increasingly complex life forms. These prehistoric creatures, preserved in the Burgess Shale, were among the first to obtain energy from the light that permeated the universe. Before they existed, the sun and stars in the night sky rose and fell without their knowledge. According to Burgess's research, the strange, worm-like picaia may have evolved a specific adaptation that allowed humans to survive. The pica, with its humble appearance, may be one of the most important animals on the planet. Not all evolutionary biologists agree that the picaia represents the earliest known progenitor of contemporary vertebrates, the order of life that includes ourselves. Picaia is particularly intriguing because it may have possessed light-sensitive cells that evolved into human eyes over hundreds of millions of years, enabling it to elude predators and thrive in the Cambrian seas. This is all speculation, but it's plausible that Picaia's remarkable, if rudimentary, capacity to sense solar light prevented humans from ever existing on Earth. Perhaps university life would not have existed here if Picaia, the one thing that has helped us understand our universe, could glance up. We have even felt the brightness of the beginning of time and had a glimpse of our roots. Understanding the universe and reading a detective story are similar because light travels through time, carrying crucial evidence that helps solve crimes. We have even glimpsed our past and seen the birth of time. Our ancestors would have been astounded by what we have seen. Galaxies frozen in time at the frontier of the observable universe, people born in faraway worlds, and our universe only seconds after it all started. Our green, blue, and brown eyes, originating during the Cambrian explosion, are incredibly fascinating because they allow us to see into the night sky, gather light from distant stars, and narrate stories about the universe. What components make up humans? Since ancient times, philosophers and scientists have diligently attempted to find an answer to this question, which is among the oldest. The story of the search for the universe's building blocks will have another chapter by the time you finish reading this book, because this work is still ongoing. Such is the power, the excitement, and the rapid advancement of modern science. This documentary explores the origins of those building blocks in the early universe, their gradual assembly into planets, mountains, rivers, and human beings by natural forces, and their fusion into more complex structures over billions of years in space furnaces. The Large Hadron Collider, LHC, is the highest energy particle accelerator at CERN, the European Particle Physics Laboratory near Geneva, Switzerland. Within this enormous machine, which has a circumference of 27 kilometers, 17 miles, proton beams collide head-on. Scientists can identify and record the resulting particles to comprehend their interrelationships. The ancient Greeks thought about what made us, despite lacking the scientific methods and tools necessary to reach a firm conclusion. This gave rise to many rival theories, some of which approached our current understanding, that we are all composed of smaller parts. The atomic hypothesis, generally attributed to two thinkers, Leucippus and Democritus, in approximately 400 BC, postulates that the smallest building blocks of matter are indivisible basic units that can be fitted together to build the world. They held that the world comprised an infinite variety of indivisible, indestructible atoms. Because they were all different shapes, they could all fit together neatly to form large objects. Thus, they created water from one kind of atom, iron from another, and human flesh from another. They thought atoms were just like real-world objects. For example, metal atoms had a certain shape that allowed them to combine to form tough substances, while water atoms were slippery. Given our understanding of this significant overcomplication, we must address it. The world is composed of smaller pieces, as their hypothesis stated, but infinite atom types are not necessary to create the complexity surrounding us. The same elements compose the Earth, the sky, fish, and humans. The field of particle physics is responsible for counting the fundamental components and figuring out how they work together. The Large Hadron Collider at CERN in Geneva is the site of this work. We found in early 2011 that of the 12 fundamental building blocks of the universe, only 3 are required to construct anything on Earth, including our own bodies. The more familiar protons and neutrons can be created by assembling these 3 constituents, also referred to as the up and down quarks and the electron. A proton is made up of 2 up quarks and a down quark, while a neutron is made up of 2 down quarks and an up quark. The basic chemical elements, hydrogen, carbon, oxygen, iron, gold, and silver, are among the 94 known to occur naturally. In turn, protons, neutrons, and electrons make up the chemical elements. One of the world's holiest rivers begins 15 miles northeast of Kathmandu, the capital of Nepal, where 3 small streams converge. The Bagmati is a swift mountain stream at its source, but it transforms into a broad, magnificent river as it passes through the Kathmandu Valley and enters the vast city of the Himalayas. One of the holiest places in Hinduism, the 5th century Pashupatinath Temple, is located in the city's eastern section, at the epicenter of the river's legendary power. Travelers from Nepal and India gather to worship and honor Shiva. Hinduism has always captivated me because it is a deep and intricate religion that combines philosophy and mythology in a bewildering way. It also produces a joyful assault on the senses through its constant and erratic juxtaposition of temples, holy sites, rituals, and daily life. This also applies to Pashupatinath. It is simultaneously bright and ethereal, a location where the sounds and colors of India collide with the serene philosophy of Tibet, and the hybrid vanishes into the high, pure Himalayan air amid the smoke from 1,000 funeral pyres lit at this hallowed site. The smell of charring flesh mingles with incense and chiming bells, while the cries of market vendors are constantly cut off by the sound of the monkey gods chanting. The Trimurti, or the triad of the 3 essential aspects of the Supreme Being, symbolized by the powerful gods Brahma, Vishnu, and Shiva, is a fundamental idea in Hindu philosophy. Lord Brahma created the universe, Lord Vishnu preserved it, and Lord Shiva destroyed it. Shiva represents darkness as an enraged god who will ultimately bring about the end of the world. However, Hinduism sees this destruction as a necessary component of life, since the old order must collapse for new things to arise. As a result, Shiva is also a fertility deity, a component of the never-ending cycle of death and rebirth that is fundamental to Hinduism. This explains why people revere the river next to the Pashupatinath temple as a place of death. Hindus believe that death and rebirth are an endless cycle, and a loved one's passing is just one stage. Cremations are a common sight along the holy Bagmati River. Following the ceremony, the chief mourner, frequently accompanied by the other attendant mourners, must bathe in the river's water. Hindus hold that the goal of a soul's existence on Earth is to perfect itself via a cycle of rebirth and reincarnation. It can only transcend its material existence and unite with the universal soul at that point. It is believed that cremating your body on the riverbank next to Shiva's Pashupatinath temple will release your soul from the worn-out body as quickly and easily as possible. The Bhagavad Gita states, "Just as a man discards worn-out clothes and puts on new clothes, the soul discards worn-out bodies and wears new ones." A Hindu tradition in Nepal requires the deceased to undergo 3 dips in the Bagmati River before cremation. The chief mourner, who is typically the deceased's first son, must bathe in the holy river's waters immediately following the cremation and light the funeral pyre. Numerous family members who participate in the funeral procession also dip in the river or sprinkle holy water over themselves. This gives the riverbank a distinctive and lively vibe. Even though death, from my British perspective, rarely parades like this, it doesn't seem insensitive to stroll among the funeral pyres in Kathmandu while friends and family go through their customs. According to Hindu tradition, the 5 elements of the human body are air, water, fire, earth, and ether. Surprisingly, modern science finds this too complex, yet its theories about the fate of these elements after death provide insight into the modern world. The cremation ceremony is based on the belief that the soul recycles and returns the elements of the deceased body to Earth. In the natural cycle of death and rebirth, death marks the end of one stage of existence and the start of another. Death does not signify the demise of the mortal flesh or the immortal soul. Regarding the atoms and molecules that make up our bodies, contemporary science fully concurs with that notion. When I pass away, my components won't magically disappear. Instead, they'll return to Earth and eventually merge into another structure. Hinduism is by no means the only religion with elaborate and poetic tales of the universe's creation and development. Almost every culture and religion has a creation story about our origins, fate, and afterlife. This implies that the human condition is inherently curious about our origins, possibly even defining them. The cremation ceremony is based on the belief that the soul recycles and returns the elements of the deceased body to Earth. Contemporary science fully concurs with this notion regarding the atoms and molecules that make up our bodies. Like the ancient philosophical traditions of antiquity, modern science has its own cosmology and physics-based creation myth. Thanks to modern science, we can learn about our origins and composition and the origins of everything in the universe. Because telling this story requires understanding the universe's history, it also satisfies the most fundamental human need, to feel like a part of something much bigger. It also teaches us that comprehending the lives and deaths of the stars, rather than our own, is the route to enlightenment. The earliest star chart still in existence, from AD 700, is the Dunhuang star chart. The British Library owns it, and its name comes from where it was discovered in the 20th century in northern China along the Silk Road trade route. The Chinese constellation customarily portrays the stars in the sky. It's simple to see why our ancestors spent so much time stargazing when you venture outside a city and encounter a genuinely dark night sky. They are a bewildering tangle, a patterned canopy of silver, clearly not devoid of purpose or significance. Ancient astronomers spent thousands of years trying to observe, record, and name as many of these far-off suns, because we now know their true nature, as they could. They also tried to capture and catalogue every light. The earliest star chart record may be more than 30,000 years old. A carved ivory mammoth tusk was found in Germany in the late 1970s, and it appears to have been imprinted with a pattern similar to the stars that make up the constellation Orion. Cave paintings found in France have shown researchers that humans were charting the night sky tens of thousands of years before the ancient civilizations of antiquity started to gradually delve deeper into the cosmos. Ancient astronomers spent thousands of years trying to observe, record, and name as many of these far-off suns, because we now know their true nature, as they could. They also tried to capture and catalogue every light. The Egyptians were among the first ancient societies to map the night sky and give names to some of the stars they saw. They noted the names of constellations and dubbed the North Star the star that cannot perish. The Sumerians and Babylonians recorded these early names and patterns and produced astronomical catalogues that enumerated and categorized stars more complexly. Greek, Chinese, and Islamic astronomers continued to create ever more complex classification systems, keeping many Arabic names for stars in use today. The starry background appeared deceptively permanent to the ancients, inspiring them to document and mythologize their observed patterns. But for the first time in history, a specific kind of transient addition to the night sky's lights was seen and recorded in AD 185. We were eventually able to tell the story of the stars' births and deaths by comprehending the nature of this uncommon and spectacular phenomenon, which went beyond simply naming the stars. Chinese astronomers saw a brightness in the sky in AD 185 that lasted 8 months and was similar to Mars's. Supernova explosions were first observed in this manner, but the remnants of this celestial event were not discovered until late 2006. The Chandra X-ray Observatory obtained this image of an object currently known as RCW-86. Red, green, and blue represent low, medium, and high-energy X-rays, respectively, in the image. Researchers figured out that RCW-86 came from the explosion of a massive star about 8,000 light-years away by looking at how the energy of the X-rays was distributed and how heavy the remnant was. The remnants of the cosmic event of AD 185, which blazed across Chinese astronomers' minds and skies nearly 2 millennia ago, were discovered in late 2006. The Chandra X-ray Observatory captured the image of the object known as RCW-86 above. This object is believed to be the glowing remnants of a supernova explosion, one of the most potent events in history. A single star can shine as brightly as 1 billion suns during a supernova, which is the last act in the life of a massive star. If the remnants of the AD 185 supernova are indeed RCW-86, then the guest star that the Chinese astronomers reported shining brightly for 8 months before disappearing from sight was approximately 8,000 light-years away. A pretty enormous distance for anything to shine so brightly in our skies. They were unaware that ancient astronomers had recorded the first conclusive proof that all stars die. Above our heads, a magnificent tale of life and death unfolds. This story begins in the vast stellar nurseries that birth new stars. Nebulae, or these productive star formation regions, are some of the most exquisite celestial formations. The Orion Nebula, seen far right, is one of these and is arguably the most studied astronomical object. Although Nicolas-Claude Fabry de Peiresc was typically credited in 1610, folklore suggests that the Mayans knew the faint spot beneath Orion's belt of stars. Most of what we know about the formation of stars comes from this intricate, constantly evolving structure. This intricate, constantly evolving structure, visible to the unaided eye in a very dark, clear sky, provides most of what we know about the formation of stars. Known by many names, including the Horseshoe or Swan Nebula, the Omega Nebula is a massive interstellar cloud spanning over 15 light-years illuminated by hundreds of bright young stars. Depending on their mass, these stars will burn for hundreds of millions or billions of years, producing a steady stream of light throughout the cosmos until their insatiable hunger exhausts the hydrogen in their cores, forcing them to enlarge and become giants. As the biggest stars get closer to the end of their lives, they become enormous giants like the Red Mirror, which is 400 times smaller than our Sun and barely makes it. These stars will eventually die, and the supernova explosion will leave behind only a faint remnant of the star. The largest stars will form black holes after supernovae, so dense that no light can escape their grip. Smaller stars will eventually become neutron stars after exploding, which we can identify by the radio waves they release during their brief lighthouse beam spins every few seconds or less. Stars that are considerably smaller than Mira won't explode. The most prevalent type of star in our galaxy is known as a red dwarf, and they are relatively cool stars. The star we have examined is the most well-known of these. This star, just over 20 light-years from Earth, has attracted much attention lately because at least 6 exoplanets are in orbit around it. The most intriguing finding is that scientists think planet Gliese 581G orbits within the star's habitable zone, which makes it a prime target for extraterrestrial life research. NASA's Galaxy Evolution Explorer captured these amazing ultraviolet photos, which reveal a star named Mira hurtling across the sky and leaving a massive trail of debris in its wake. Mira will repurpose these seeds to form new stars, planets, and life as they move across our galaxy. This molecular cloud, also known as the Horseshoe or Swan Nebula, is frequently called the Omega Nebula because of its shape, similar to the Greek letter omega. The surrounding gas glows due to ultraviolet light from a cluster of massive young stars buried within the nebula. We took this picture. We captured this image using the 3.6-meter, 11.8-foot telescope at the European Southern Observatory in La Silla, Chile, one of the most studied astronomical objects and a stunning structure in the sky. Iron from another and human flesh from another. They thought atoms were just like real-world objects. For example, metal atoms had a certain shape that allowed them to combine to form tough substances, while water. This striking configuration, which consists of more than 3,000 stars in various sizes, is visible to the unaided eye in a clear, dark night sky. This intricate, dynamic formation has given scientists important new information about the formation of stars. Venus's transits of our Sun are not common. They happen only twice every 8 years and will not happen again for 100 years. A new transit is scheduled. We have scheduled a new transit for 2012. The previous one occurred in 2004. The next one will be in 2116. Every cosmic structure in breathtaking detail reveals a different aspect of the star's life cycle. However, a deeper revelation comes from realizing that stars exist. They are our building blocks, the ultimate source of all but the most basic atoms sought after by Leucippus and Democritus. We must briefly detach from the skies and firmly return to Earth to understand how the stars could be vital to our existence. Understanding essential makeup is the first step toward comprehending the origins of our own lives. The shadow of the world's tallest mountain range is the most beautiful and arguably the most instructive place on Earth to start this journey. The Himalayan range, which contains 9 of the 10 highest mountains on Earth, is a land of giants, with over 100 peaks rising to over 7,200 meters, 23,620 feet. 45 of the top 50 peaks in the world are located in the Greater Himalayas, among the 94 known to occur naturally. In turn, protons, neutrons, and electrons make up the chemical elements. One of the world's holiest rivers begins 15 miles. For all their grandeur, these mountains were quite different a few tens of millions of years ago. The Himalayas are the largest and youngest mountain range in the world. The Himalayas were non-existent until 70 million years ago, a very short period in geological terms. Mountains were sculpted by the tectonic plates of Earth, which moved in an unrelenting geological frenzy, and human flesh from another. They thought atoms were just like real-world objects. For example, metal atoms had a certain shape that allowed them to combine to form tough substances, while water atoms were slither and human flesh from another. They thought atoms were just like real-world objects. For example, metal atoms had a certain shape that allowed them to combine to form tough substances, while water... Finding the proof of this incredible journey is relatively easy. Any piece of Himalayan limestone has a granular, chalky structure that can be seen up close. You are looking at the bodies and shells of coral and polyps that perished millions of years ago in a long-gone ocean, the petrified remains of marine life. These biological remnants quickly solidify into rock when exposed to moderate pressure and a short timescale. While the biological sedimentary form is more common, direct precipitation of calcium carbonate from water can also form limestone. We are certain that the Himalayan limestone is primarily biological because fossils were discovered at Mount Everest's summit. Perhaps no better illustration exists of the endless recycling of Earth's resources since the planet's formation nearly 5 billion years ago. We humans are also an integral part of that system. Of market vendors are constantly cut off by the sound of the monkey gods chanting. Infinite atom types are not necessary to create the complexity surrounding us. The same elements compose the Earth. Everything in the universe has the same fundamental elements, which explains how life can develop from rocks on Earth and how living things will eventually die and return to rocks. The periodic table will evoke many people's strong memories of science labs in schools. In its most basic form, this chart lists the chemical elements, which are fundamental substances and are thought to be the smallest units of matter in the universe. But this table is much more than a simple inventory. Even though elemental theories of matter were first proposed in Greece, it was Dmitry Mendeleev, a Russian chemist, on March 6, 1869, who finally controlled the ever-growing list of matter's fundamental components. Mendeleev's creative genius lay in organizing the list of the 66 elements known at the time into a table based on their chemical characteristics. During this process, the table forecasted the existence of 8 undiscovered elements and neatly arranged them based on their properties. All 8 elements, including gallium and germanium, were discovered over the following 30 years, and scientists discovered that each one had the precise characteristics that Mendeleev's table had predicted. Mendelevium is the element that honors the father of the periodic table. In 1955, researchers at the University of California, Berkeley, discovered the 101st element, a Russian US. In April 2010, the team successfully synthesized and detected unanseptium, the most recent of the 118 elements. Earth naturally contains the first 94 periodic table elements, from hydrogen to plutonium. While we can only artificially create the remaining 24 elements with a minimal lifespan, nature uses them as its building blocks. It is possible to explain biology and chemistry using these 94 elements without understanding the fundamental structure of protons, neutrons, electrons, and quarks. This is because elements require extreme heat and energy for disintegration, which can only occur naturally in the cores of stars. Understanding the genesis of these 94 elements is the first step in our journey to explain our origins. To begin with, though, we need to figure out how we know that everything in the sky is composed of the same materials as the Earth. Despite knowing only one other location in the universe, we can identify every star, planet, and moon. Neil Armstrong and Buzz Aldrin became the first humans to set foot on a different planet on July 21, 1969. They walked on the moon for 2 hours, 36 minutes, and 40 seconds. But they only did one of their most significant scientific experiments for the final 30 minutes. Using simple geological instruments, Buzz Aldrin extracted history's most well-known rock samples by driving 2 core tubes into the lunar surface. They had amassed 22 kilograms, 47 pounds, of lunar loot by the time they had completed pounding and gathering samples. They lifted their scientifically valuable cargo on board using a pulley system, shut the hatch, and retired for the night. The United States could claim to have achieved the greatest and most glorious political victory in human history as the 2 astronauts slept beside the priceless lunar rocks. A political victory also happened to be a triumph for humanity for a brief moment. It is not well known that a Soviet spacecraft was in lunar orbit while the Apollo 11 lunar module was resting on the moon. The third attempt by the Soviets to land on the moon and gather samples of lunar rock was the unmanned Lunar 15. Launched 3 days before Apollo 11, Lunar 15 was the last attempt to win the competition between scientists to retrieve rock samples from another planet. Unfortunately, not long after Lunar 15's successful descent to the moon's surface, it collided with it. The moon rocks that only Apollo 11 brought back are still being examined in the high-security laboratories of the Lunar Sample Building in Houston, Texas. After 40 years of research, these rare specimens of extraterrestrial geology certainly bear striking similarities to rocks on Earth. The moon's surface mostly comprises common elements that form rocks, like oxygen, silicon, magnesium, iron, calcium, and aluminum. It doesn't contain any materials that are specific to Earth. We have landed on Mars, Venus, the comet Tempel 1, the asteroid Itokawa, and Saturn's moon Titan since the triumph of Apollo 11. We have also parachuted into Jupiter's atmosphere. More familiar protons and neutrons can be created by assembly. We have been able to thoroughly investigate the geology of Mars, our closest neighbor, thanks to 8 landings there. We now know that Martian soil is somewhat alkaline and contains elements like magnesium, sodium, potassium, and chloride. Mars is also rich in iron, which has oxidized to form its well-known rusty red color. We also know that Mercury is a big iron ball with a thin crust primarily made of silicon, and Venus has a thick atmosphere laden with sulfur. We have found that Neptune has a lot of organic molecules like methane, which is abundant on Earth, even though it is billions of miles away from Earth at the edge of the solar system. We keep finding that while there is always more to learn about our solar system, there are never any new elements to uncover. This is not surprising from a scientific perspective, since we have already discovered the whole set of light elements in nature, as demonstrated by Mendeleev's table a long time ago. From the adventurer's perspective, one must see to believe. Physics would have to change if we found something on another planet that defies Mendeleev's plan. For the rest of the universe, what does this mean? To what extent are these elements present throughout the vast universe? Are all composed of smaller parts? The atomic hypothesis. This is a valid question. Regardless of the strong theoretical physics arguments, we shouldn't just assume that everything that exists billions of light years away at the edge of the visible universe functions exactly as it does here. The best ways to verify reality are through experimentation and observation. Because they were all different shapes, they could all fit together neatly to form large objects. Thus, they created water from one kind of atom, iron from another, and human flesh from another. They thought atoms were just like real-world. I recreated it by Robert Bunsen and Gustav Kirchhoff, who significantly influenced the theory of a basic campfire. I threw the copper into the fire, which burned with a magnificent blue flame, just as they had discovered 150 years before. Our solar system central star, the Sun, is 150 million kilometers, 93 million miles, from Earth. After that, it would take more than 4 light years, or 40,000 billion kilometers, to reach the closest known star, the red dwarf Proxima Centauri, 25,000 billion miles. We have learned much about Proxima Centauri since its discovery by Robert Innes in 1915 at the Cape Observatory in South Africa. Proxima Centauri is part of a triple star system that includes Alpha Centauri A and B, 2 nearby binary star systems. Over the past century, we have measured its mass, diameter, and brightness, despite being invisible to the unaided eye. Even though the light that travels across the universe to reach us is the only communication we have with these nearby stars, or with any star other than our Sun, we have accomplished much more than just compiling a list of their essential characteristics. The exact components of every star visible in the sky are encoded in the light that descends upon Earth, providing us with knowledge of their makeup. A particularly lovely feature of the elements makes it all possible. Isaac Newton's 1670 work began reading star histories in their light. Newton proved in his theory of color that light comprises a spectrum of colors and that the sun's white light can be divided into color components using a straightforward glass prism. While adjusting some of his cutting-edge telescopic lenses and prisms, German scientist Joseph von Fraunhofer made an astounding discovery about the solar spectrum nearly 150 years later. Basic units that can be fitted together to build the world. They held that the world comprised an infinite variety of indivisible, indestructible atoms. Fraunhofer had no idea how significant this discovery would be then, so she meticulously and extensively mapped their locations. Later, he noticed black streaks in the light coming from other stars, planets, and the moon. We now refer to these as Fraunhofer lines. These lines finally found meaning thanks to additional research by 2 more of the greatest German scientists of the 19th century, Robert Bunsen, probably best known to schoolchildren worldwide for creating the Bunsen burner, and Gustav Kirchhoff. They accurately assumed that the black spectral lines represented the chemical element fingerprints in the Sun's atmosphere. The light of our star has traveled 150 million kilometers, 93 million miles, across space to bring the signature of its components to us. When Kirchhoff and Bunsen noticed that gases on Earth emit very specific light colors when heated, they made a purely empirical discovery. It's fascinating to note that these colors are independent of temperature and solely depend on the chemical makeup of the gas. Specifically, every element in the chemical world has a distinct color palette. Copper emits a melancholic emerald green hue, sodium emits a deep yellow hue, and strontium burns with a stunning red color. The 2 German scientists also observed that the glowing colors of the elements precisely matched the missing black lines in the solar spectrum. For instance, the 2 distinct yellow emission lines of hot sodium vapor are exactly matched by 2 black lines in the yellow portion of the sun's light. This combination of 2 slightly different yellows, the color of sodium streetlights, will be recognizable, destructible atoms. Because they were all different shapes, they could all fit together neatly to form large objects. Thus, they created water from one kind of atom, iron from another, and human flesh from another. Only at the turn of the 20th century was there an explanation for the peculiar behavior of the elements. The answer is found in quantum mechanics, and the development of quantum theory was greatly aided by the spectrographic work of physicists and chemists like Kirchhoff and Bunsen. Elements produce and absorb light when the electrons around their atomic nuclei oscillate. Unlike planets around a star, the realization that electrons can only exist within specific, highly restrictive orbits around a nucleus was the pivotal discovery that led to the development of quantum theory. LIDAR, LHC, is the highest energy particle accelerator at CERN, the European Particle Physics. Additionally, their wave-like properties greatly limit their confinement around the atomic nucleus. An atom absorbs light at the microscopic level, causing an electron to jump to a new, more energetic orbit. An electron returns from a higher energy orbit to a lower energy orbit, releasing light. The energy of the light absorbed or emitted must precisely match the energy difference between the lower and higher orbits. German scientist Joseph von Fraunhofer recorded 574 dark lines in the solar spectrum at the beginning of the 1800s. This diagram visually represents these Fraunhofer lines. According to spectrographic studies, Sirius, the dog star, is metal-heavy, with 3 times the Sun's iron content. How wonderful that the light from those distant stars can illuminate those burning worlds' compositions. We can tell by looking at Polaris, the top and middle pole star, which has roughly the same heavy element abundance as our Sun, but noticeably less carbon and much more nitrogen. Polaris is located 430 light-years away, while Vega, bottom, is the second brightest star in the northern sky. It only has roughly 1/3 of the solar metals. But quantum. However, according to quantum theory, we cannot always view light as a wave. Like electrons, we cannot always view light as a stream of particles or a wave. We refer to these particles as photons. The important thing to remember is that different light colors are associated with different energies of photons. Red photons have a lower energy than yellow photons, which have a lower energy than blue photons. Each element can only absorb specific photons to shift its electrons into higher energy orbits because their atoms are in different orbits around the nucleus. On the other hand, electrons that descend from higher to lower energy orbits will only release photons of a specific energy and, consequently, a very specific color. This is evident when the components emit or absorb specific light colors. We are actually witnessing the structure of the atoms. Hundreds of Fraunhofer lines can be seen in a spectrum of light from our Sun. These lines represent various elements in the solar atmosphere that absorb light as it travels through. Every element's signature, from sodium in yellow to iron and magnesium in red to the so-called hydrogen alpha line in yellow, is encoded in the solar code. You can determine precisely which elements are present in the Sun by closely examining these lines. The Sun comprises about 2% other elements, 28% helium, and 70% hydrogen. It is important to emphasize that this theory can be applied to any star in the sky, not just the Sun, allowing us to measure the components of their atmospheres with remarkably high precision. Isn't it amazing that we can tell what makes those burning worlds what they are just by looking at the light from those far-off stars? With these spectrographic studies of extraterrestrial light, we have verified our scientific intuition. Everywhere we look, we see only the signatures of the 94 naturally occurring elements we have gathered and identified on Earth. Because we are all fundamentally composed of the same materials, we are inextricably linked to the entire universe, with hundreds of billions of stars spread across billions of galaxies. There's a straightforward explanation. Understanding the universe's early moments helps us understand where we came from. Of India collide with the serene philosophy of Tibet, and the hybrid. The universe was incredibly hot and dense initially. No words in science adequately describe it. It was lovely in a very tangible way. Nothing existed. It seemed the same from every perspective. Though it's a challenging idea to comprehend, we can learn something about the early universe's history by observing how water, one of the most prevalent substances on Earth, behaves. One of Earth's most abundant substances, water, can create some of its most beautiful geological features. One of the amazing things water can do is the El Tatio geysers in Chile. Hydrogen and oxygen are the two chemical components of a water molecule. When oxygen and hydrogen atoms are separate and unpaired, they exhibit symmetry. The term symmetric here refers to the atom's consistent appearance from any viewing angle. This is known as rotational symmetry in physics. A perfect sphere has perfect rotational symmetry because it looks the same whether you spin or look at it. This rotational symmetry disappears when an oxygen atom combines two hydrogen atoms to form a water molecule, H2O. Water molecules have their hydrogen and oxygen atoms angled at a specific angle of 105 degrees, which gives them a unique shape. A physicist would argue that the unique orientation of the water molecule breaks the symmetry. By cooling down all the molecules of water until they cling to one another and solidify into ice, we can further break the symmetry of the liquid. Now, the ice crystals are stunning and nearly unfathomably complex, with a lot of structure and intricacy, concealing the original atom's perfect symmetry and the water molecule's unique but basic symmetry. Water covers approximately 70% of the Earth's surface. Because they were all different shapes, they could all fit together neatly to form. I held a sheet of glass in the steam from the geysers and watched ice crystals form on it as I walked through the ground's pools of water. The universe was transitional, like steam turning into ice and chaos into order. The structure and substance of all matter particles first appeared at this transition. The important thing to remember is that we only cooled the water. We did nothing to disrupt its symmetry. Thus, even though it seemed like a skilled sculptor made complex designs on the ice, this beauty and intricacy came from perfectly symmetric building blocks. This process is known to physicists as spontaneous symmetry breaking, and our understanding of the early universe is based on this concept. Infinite variety of indivisible, indestructible atoms. Because we're still working on it. We also need to find out why it started in such a form. This is still a mystery that fuels the curiosity about fundamental physics. The first major event we can address in any scientific language is the Planck era, which occurred an amazing 10 to the power of 43 seconds following the Big Bang. The full expression of the Planck era has 42 decimal places. We reach this figure by tying it to the gravitational force's strength. Gravity is ultimately so small since we do not know why it is so weak. Now, there was only energy and the superforce. There was no matter. Gravity, the strong and weak nuclear forces, and electromagnetism, the four fundamental forces of nature that we now know, were one and the same force, a single superforce. A physicist would call this a highly symmetric scenario. As the universe fast cooled and grew, it underwent events breaking symmetry. The first happened at the end of the Planck era, when gravity broke the perfect symmetry and separated from other natural forces. 10 to 36 seconds following the Big Bang marked another event, breaking perfect symmetry. This resulted in the separation from the other forces, the strong nuclear force, which holds the quarks in protons and neutrons together. Between 10 and 32 seconds, the universe grew by a factor of 1026, or 100 million times, starting the extraordinarily violent expansion known as inflation. Between 10 and 32 seconds, filled the world. They held that the world comprised an infinite variety of indivisible, indestructible atoms. Our research indicates that the basic building blocks of our universe are hydrogen and helium. This narrative has a strong theoretical drive, but has been mainly untested experimentally until now. Recreating and observing this era at CERN's Large Hadron Collider allows us to be within reach of the next major symmetry-breaking event, occurring 10 to 11 seconds following the Big Bang. The last two forces of nature, weak nuclear force and electromagnetism, are separated by electro-weak symmetry breaking. The subatomic components of everything we observe nowadays acquire mass during this process. The most generally accepted theory for this process is the Higgs mechanism. Hence, one of the main goals of the Large Hadron Collider project is to identify the matching Higgs particle. Right now, we have quite a strong theoretical and experimental foundation. We can now confirm our grasp of physics by running particle accelerator experiments, which enables us to precisely know what transpired in the universe. Starting at the end of the Planck era, a series of symmetry-breaking events resulted in the creation of the familiar particles and forces in the universe nowadays. Analogous to early universe spontaneous symmetry breaking is the change from water vapor to liquid water to ice. Complicated patterns arising naturally, just as a result of the temperature decline, hide the underlying symmetry of the initial state. Much as the apparently limitless complexity of snowflakes hides the simple symmetry of oxygen and hydrogen atoms. The variety of natural forces and subatomic particles we now understand as the building blocks of the early universe obscures their symmetry. Protons and neutrons require one last step. Quarks had cooled enough to be joined by a strong nuclear force to form protons and neutrons. This began roughly a millionth of a second after the Big Bang. The most fundamental element, hydrogen, consists of one proton. Thus, the first chemical element arose just a millionth of a second into the universe's existence. 3 minutes later, the universe turned cold enough for the protons and neutrons to cling to one another and create helium. With a nucleus comprising 2 protons and 1 or 2 neutrons, helium is the second simplest element. Also in minute concentrations were the third and fourth simplest elements, beryllium, 4 protons, and lithium, 3 protons. And here, the process came to an end. 3 minutes later, the universe consisted of roughly 75% hydrogen, by mass, and 25% helium, with the 4 distinct forces we know: gravity, the strong and weak nuclear forces, and electromagnetic. This is the story of developing the most fundamental chemical elements in the early universe and consequent events involving symmetry breaking. Our knowledge of the structure of matter has evolved during the past century. Originally thought to be the building blocks of life, Rutherford's well-known diffraction experiment showed that matter was essentially composed of space, and that each atom had a dense, tiny nucleus surrounded by an electron cloud. Later research revealed that every nucleus consisted of protons and neutrons, with each proton made up of up and down quarks. According to scientists, all matter consists of 9 particles, 4 forces, and the hypothetical Higgs boson. These are supposed to be the smallest particles that are conceivable. Searching for the basic constituents of matter has been done using matter colliders, which can create the very high energies required to replicate the temperatures in the early universe when these subatomic particles existed. We can split the history of the universe into several phases depending on the physical environment of the time. The universe changed fast in the first fraction of a second into a turbulent mixture of exotic particles and energy. The first protons and neutrons finally developed as the first atoms' nuclei, mostly hydrogen and helium. The events slowed down after the cosmic microwave background emission, which occurred some 400,000 years following the Big Bang. According to present knowledge, the universe will grow endlessly before disappearing into darkness in the erratic future. The easiest example, so appropriate for young children, shows how all the chemical elements in the universe combine. all you need to understand how the structure has developed is a pot of bubble mixture. Blowing one bubble allows you to return to the beginning of time when the proton was the only entity existing in the universe. The simplicity of this universe is a mystery at the core of science. We do not yet know why it is simple. The building of the elements exposes the great simplicity under all the incredible complexity. Over human history, the evolution of civilization has been intimately linked with the identification and use of specific chemical elements. Thought to have been mined and fashioned by humans 11,000 years ago, copper's special qualities ushered in a new age of technology and the change from stone to metal weapons and tools. 4,000 years later, iron, the foundation of industrial civilization today, underwent the same process when mixed with carbon to create the alloy steel. Their physical characteristics made these two elements important in our history. Copper is probably the first metal humans use, since it is one of the few naturally occurring metals in their pure form and has an unreactive chemical makeup. It is also flexible, soft, and easy to shape tools and weapons. Copper forms the alloy bronze using another metallic element, tin. Zinc forms brass when combined with copper. Surprisingly, iron is the most plentiful element on Earth. It ranks fourth among the elements found in the rocks that comprise the crust of the planet. Though more difficult to extract and work with, iron is a common material used in weapon manufacture since it is harder and lasts longer than bronze. Just a few places apart on the periodic table, these two metals have had a major influence on human history. Iron, Fe, and copper, Cu, are elements 26 and 29, respectively. The first humans to use these metals would not have known why the two elements looked physically similar yet different. What then distinguishes them most fundamentally? The answer is very simple. As was already noted, the atoms of each element consist of three basic components: protons, neutrons, and electrons. We do not have to consider quarks inside protons and neutrons, since they remain locked away at the temperatures we know on Earth. We can thus ignore them when discussing earthly chemistry. Chargeless neutrons vary, while all elements have the same number of protons, p, in the nucleus and orbiting electrons. One of the first four elements we have thus already come across is hydrogen's atomic nucleus, which consists of one proton. An electron in orbit around the positively charged proton forms a hydrogen atom. An electron has a negative electric charge, unlike a proton. Hydrogen's atoms are hence electrically neutral. Why the electron and proton have opposite charges remains unknown. This becomes even more surprising when one considers the proton's quarks. The proton consists of three quarks, up quarks and down quarks. Whereas the up quark has +2, 3, the down quark has a 1, 3 electric charge. The electron has a 1 charge. Consequently, when taken together to form a proton, everything balances properly. Consisting of two down quarks and an up, the neutron has no electric charge. This cannot be a coincidence. Explaining it is one of physics's main challenges in the 21st century. Although their atomic nuclei contain different numbers of protons, the chemical characteristics of various elements are not changed by their neutron count. The basis of chemistry is the orbit of electrons around the nucleus, the count of which matches the count of protons. The hydrogen atom consists of one proton and one electron. Deuterium is another variant of hydrogen. Deuterium still only has one electron. Thus, its chemical properties remain unchanged even with the neutron joining the proton inside its nucleus. Technically speaking, deuterium and hydrogen are separate isotopes of the same element. Helium-3 and helium-4 can be formed with 1 and 2 neutrons, since helium atoms always have 2 protons and 2 electrons. Next comes lithium, with 3 protons, 3 electrons, 3 or 4 neutrons, and occasionally more. Carbon has 6 protons, varied neutron counts, and so on. Though the count varies, the nucleus of every element has at least one additional neutron and proton, with electrons helping to create the bond, even though they lack electric charge. The strong nuclear force firmly ties the nucleus and neutrons together. Electric charge influences the nucleus. Positively charged protons try to split it apart by repulsion of one another. Heavier nuclei often feature more neutrons than protons, since neutrons are insensitive to this issue. Thus, it is easy to build chemical elements. Add 3 protons and some neutrons to make the iron nucleus copper. The procedure is easy. Nature can achieve this even if it is easier said than done, since the first 4 chemical elements were present when the universe was just a few minutes old. Though the building blocks were already there, nature arranged the heavier elements later. 2 of the best physicists had already lost enthusiasm for the idea years before the Manhattan Project developed and unleashed the most terrible weapon in history. Before any nuclear bomb was developed in 1941, friends and colleagues Edward Teller and Enrico Fermi, who would subsequently join the Manhattan team, had already lost enthusiasm. Fission bombs, which separate the nuclei of very heavy elements, in the case of the Hiroshima bomb, uranium, and in the case of the Nagasaki bomb, plutonium, produce lighter elements such as strontium and cesium. Here, we reverse the components. The neutrons emitted during the split of a uranium or plutonium nucleus cause other nuclei to split. This is the way a nuclear chain reaction proceeds. This nuclear binding energy is stored in the strong nuclear force field, which comprises protons and neutrons within the nucleus. Every time a heavy nucleus splits, it releases a lot of energy. But even in the very early stages of the Manhattan Project, years before the idea of a fission bomb was a tangible reality, Enrico Fermi felt that the possibility of creating a far more powerful type of bomb was real. After fixating on his friend's idea, Edward Teller worked for 10 years building and designing a machine capable of generating the most powerful explosions ever created on Earth. Following this success, Teller rose to become known as the father of the hydrogen bomb. Fermi saw the outcome of his conversation with Teller on November 1st, 1952. The first successful hydrogen bomb test Ivy Mike conducted on the Pacific Ocean atoll of Enewetak, thought to be 450 times more powerful than the bomb dropped on Nagasaki. The explosion had a crater 2 kilometers, 1 mile wide, a fireball more than 5 kilometers, 3 miles wide, and destroyed the small atoll. Not there when the bomb exploded was Stanislaw Ulam, another Manhattan scientist Teller had collaborated with on its design. Rather, he watched a seismometer thousands of miles distant while seated in his Berkeley, California office. Given the strength of the explosion, he could clearly see the shockwave from the solace of his office. He gave his colleagues strange instructions to tell them about the success. The Ivy Mike experiment marked the first synthetic nuclear fusion event. Nuclear fusion is the exact opposite of fission, combining 2 atomic nuclei to produce one heavier element. The hydrogen bomb reproduces the assembly of hydrogen into helium that occurred in the first phases of the universe's evolution. All 5 of the main nuclear weapon states use the Teller-Ulam design for the hydrogen bomb detonated on Enewetak nowadays. When combined with the other bomb stages, the fusion component of the design releases a degree of destruction never seen before, even though it simply accentuates the explosive force of the design. These 2 approaches of producing fresh elements and releasing vast amounts of energy differ completely. First is fission, that is, the splitting of a heavy element. Lighter elements stick together in the second fusion process. How, then, can both of these systems release energy? This seems at odds. Of course, given this is how nature operates, there is no contradiction here. Crucially, the ability of the strong nuclear force to hold protons and neutrons together, as well as the electric repulsion of the protons in the nucleus, balance each other. Given two opposing forces at work, one trying to blow the nucleus apart and the other to glue it together, you could assume that there must be a balancing point, an ideal mix of protons and neutrons balanced between attraction and repulsion. Iron and nickel are two elements quite near to the ideal stability mixture. Combining them will help us release energy and produce lighter and more stable elements. Through disassembly, we can release energy and stabilize heavier elements. Surrounded by the incomprehensible power of nuclear explosions, a clear blue sky. To be quite accurate, the stability of the elements depends on factors other than only the balance between the nuclear and electromagnetic forces. The form of the nucleus and quantum mechanical factors help to balance protons and neutrons. See semi-empirical mass formula on Google. Have fun! Though it is the height of human technological ability, fusion is the most natural occurrence on Earth. Apart from the events during the Big Bang, this process occurs all around the universe. It happens continuously and lights the universe millions of miles above our heads. Including our Sun, fusion drives every star in the heavens. Looking up at a clear blue sky, the incomprehensible power of nuclear explosions surrounds you. Deeply buried 800,000 kilometers, 500,000 miles, below the surface of the Sun, where temperatures can reach 15 million degrees Celsius, hydrogen fuses into helium. In a second, the Sun transforms 600 million metric tons of hydrogen into helium, releasing as much energy as humans will need in the next million years. The solar system is heated and lit by this energy, making the stars shine. Among the most clear instances of fusion are the brilliant Sun. Like every other star in the heavens, it is driven by a mix of hydrogen and helium. The Sun generates energy for all life on Earth through hydrogen to helium conversion. Despite its great power, the Sun only turns the simplest element, hydrogen, into the next simplest, helium. Driven by this reaction and fueled by hydrogen, every star in the universe begins life and repeats this process across the night sky. Consequently, we completely understand how to combine the second simplest element, helium. The stars did it in the early universe. We can do it on Earth. Still, we need more data to clarify the source of the other 92 naturally occurring elements. There has to be plenty somewhere in the universe, since the other elements are common and define our planet. Among the billions and billions of atoms that make up us are iron, magnesium, zinc, and, of course, carbon, the atom most important for life. Every human being on Earth consists of almost a billion carbon atoms. That is an incomprehensible number of carbon atoms missing from the early universe. The answer has to be nuclear fusion. The stars make sense where one looks. The first stars developed some 100 million years after the Big Bang. Their mass controls their hydrogen fuel burning rate. Mass brightens a star and reduces its lifetime. Understanding the formation of the heavier elements depends on knowing what happens to stars running low on hydrogen fuel. The biggest stars might not show up for a few million years. Stars like our Sun may take 10 billion years, but the universe has existed long enough to allow the life and death of many star generations. Although stars like our Sun do the opposite, you would think a star would progressively fade as its hydrogen stores ran out. After using the core as its beating heart for millions or billions of years, a star swells up to perhaps hundreds of times its starting size when it runs low in hydrogen. These are red giants, we say, of stars. Just 500 light-years from Earth, the red giant Alpha Orionis, also known as Beetle Juice, is among our nearest cosmic neighbors, and this is the 9th brightest star in our night sky. Beetle Juice, which is readily seen with the unaided eye because of its brightness and reddish tint, has long been familiar for stargazers. Sir John Herschel studied the star extensively in the 19th century, recording the remarkable brightness variations. But it was only when the three Mount Wilson Observatory California astronomers tried to gauge its diameter that we realized this was no normal star. Using a custom-built telescope, Albert Michelson, Francis Pease, and John Anderson measured the scale of this red star using interferometry. Measuring the angular diameter, that is, the apparent size of an object from our perspective on Earth, Albert Michelson, Francis Pease, and John Anderson came to the conclusion that Beetle Juice is a real giant in every respect. This star is shockingly huge, even having about 20 times the mass of our Sun. If Beetle Juice were positioned at the solar system's center, it would eclipse our Sun. Betelgeuse would, in fact, cover everything out to Jupiter outside the orbit of Earth. Current estimates place its diameter at roughly 800 million kilometers, 500 million miles, and it is a great ethereal wonder that would fill our solar system with a single wispy star. Though Betelgeuse is a great wonder, one wispy star would occupy our solar system. We can study her in great detail, given Betelgeuse's great scale and close proximity. In 1996, the Hubble Space Telescope recorded the first direct picture of another star, exposing surface features and disk of Betelgeuse. We have examined its atmosphere in ever greater detail and even visualized sunspots on its surface. But the red giant's surface does not reveal the origin of the heavy elements. We must venture far into its dying core to understand that. Betelgeuse is one of our closest neighbors and the 9th brightest star in our galaxy. From Earth's unaided view, its brightness and reddish tint make it easy to find in the night sky. Making a television documentary always requires finding graphic means to tell complex stories. We searched all over for backgrounds and analogies for wonders of the universe, but the one that suited me the best was an abandoned jail in Rio de Janeiro, Brazil. The building was a brick skeleton, a gutted husk. If windows had existed, they were all gone. There were 20 or 30 concrete bunk beds in the close-quarters dormitories the cells housed. Every cell included a tiny bathroom. Some even showed their dedication to privacy by stringing frayed cloth across the door. The cell walls were a hideous patchwork of ripped colors strewn with glitz girls and the odd football team. For two reasons, it troubled me. First, the idea of being imprisoned there is inevitable. Years spent in a steel and concrete cage is inappropriate in Rio, a hot, muggy city. Less sophisticated, the second measure consisted of wiring live explosives around the prison. Inside the shell, the brilliant outside was invisible against the black inside, pressing and brilliant like a stellar surface. The light won't show through. It stays outside the city as well. I sensed the analogy as I descended cement-dusted hold stairways into the dark core of the dying star. Far from the light of the surface, inside a violent, condemned structure, the painstaking assembly of living things takes place. At this point, the star transforms from material consumer to producer. Stars have an unstable equilibrium. Their gravity compresses them, overcoming the electromagnetic repulsion between the hydrogen atoms to fuse into helium and heat them. By releasing energy, this process preserves the brightness of the star. When the hydrogen runs out, the star undergoes a dramatic structural change. The outward pressure vanishes, and gravity takes back control. The core collapses rapidly to leave a hydrogen and helium shell. A fresh fusion starts when the contracting core temperature reaches 100 million degrees Celsius. Once helium nuclei can overcome their electromagnetic repulsion and approach near enough to fuse at these temperatures, the star begins to burn helium. Two major effects of this shift from hydrogen to helium fusion are quick star swelling and stabilizing of the star. Its life as a red giant is just getting started. Second, it generates the components indispensable to life. the only outcome of two helium nuclei, each with 2 protons and 2 neutrons, should be the isotope beryllium-8, which consists of 4 protons and 4 neutrons. In the extreme heat of a dying star, where the core temperature reaches over 100 million Kelvin, this unstable beryllium isotope degrades rapidly, but these nuclei survive long enough to fuse with a 3rd helium nucleus to form the valuable element carbon-12. The dying star's core generates all of the carbon in the universe and every carbon atom seen in all living entities on Earth. A building's supporting elements and structure degrade with time, much like a dying star. Amazing planetary nebulae are produced when a dying star explodes at the end of its life. It wrecked the prison block in seconds, the same speed at which a red giant star collapses. Alchemy generates carbon but does not terminate the helium-burning phase. This is so because, under the same scorching stage of a star's life, the conditions allow a helium nucleus to attach itself to a newly formed carbon nucleus to produce another element required for life. Apart from being the 3rd most often occurring element in the universe, following hydrogen and helium, oxygen is a vital component of water, the solvent of life, and accounts for 21% of the air we breathe. Remember that this vital gas comes from a quite different source than what we would regard as livable, as you inhale 2.5 grams of oxygen every minute. A star's carbon and oxygen generating line finishes quickly about its lifetime. Fusion ends for many stars when the core's helium supply runs low for around 1 million years. Like our Sun, an average-sized star has reached the end of its active lifetime. When our Sun reaches this stage, which should occur in around 10 billion years, there won't be enough gravitational energy left to compress the core further and resume fusion. Instead, massive pressure points will build up as the star becomes more unstable until the stellar atmosphere explodes, launching the precious hydrogen, carbon, and oxygen load into space. In just a few tens of thousands of years, a dying star will develop a planetary nebula, one of the most beautiful constructions in the universe. Following this brief cosmic light show, an average star will become no bigger than Earth. Though Beetle Juice and other massive stars are far from done, such stars and billions like them wind up as white dwarfs. If a star's mass is half that of our Sun, it will continue down the chemical production line. As helium fusion fades, gravity takes the front stage, and the core collapses. The 3rd stage of building the components in our universe starts with increasing temperature. 2 carbon atoms fuse sodium. Carbon fuses with helium to form neon, as temperatures rise to hundreds of millions of Kelvin. Magnesium is formed from neon fuses, including more helium. The temperature rises with increasing elemental components added to the cooking pot, producing one heavier element after another. As the core collapses, the temperature rises, and the consequent fusion stage begins. Layers of recently generated elements remain behind. Now that the first 25 elements have been generated inside the star, the rogue production line pauses at the 26th element, iron, generated by a complex series of fusion events driven by silicon. With its temperature at least 2.5 billion Kelvin, the star has nowhere else to go. The star cannot release more energy by adding protons or neutrons to iron. It has attained nuclear stability. In a desperate attempt to oppose gravity and release the last of the nuclear binding energy, the last stage of iron production, which lasts just a few days, turns the heart of the star almost pure iron. After its core fuses into iron, where the fusion process stops, the star has only seconds to live. The star has to give in to gravity and produce a planetary nebula. Like many planetary nebulas, IC 4406 is a dying star with great symmetry. Dubbed the Retina Nebula, some have likened its dust tendrils to the eye's retina. Earth and the Calabash Nebula lie about 5,000 light-years, 4,700 trillion kilometers, 2,900 trillion miles apart. This image of star material expelled was taken with the Hubble Space Telescope. From Earth, the Eskimo Nebula gets its name from its appearance, which resembles a head with a fur-lined hood. Astronomer William Herschel first encountered it in 1787. The necrohelix is shown here in composite form. Although new data shows the helix consists of two gaseous disks, this planetary nebula appears from Earth like a donut. Scientists first encountered the young planetary nebula Mycen 18 early in the 20th century. However, this January 1996 Hubble Telescope picture revealed the nebula's finely etched hourglass form. William Herschel found the Cat's Eye Nebula, NGC 6543, in 1786, one of the first planetary nebulae. This one is among the most complex nebulae in the universe. Imaged on July 20th, 1997, MZ3 has been named the Ant Nebula because, from Earth-based telescopes, its outline looks like an ant's head and thorax. However, upon closer inspection, the ant's body consists of two blazing lobes. This planetary nebula was discovered by Czech astronomer Lubos Kohoutek under the name Kohoutek 455, also K 455. It is special because of its multi-shell construction. One of the few still in California now, the 16-1 mine was the hub of the huge American gold rush. Digging gold there alongside the miners opened their eyes. Looking at what seemed to be common rocks, I saw glints and glimmers of a familiar yellow coloring, revealing the priceless hidden gold lode of the stones. Forming in the star's centers, the first 26 elements disperse over the universe during their unavoidable collapse. But what about the other 72? Many of which we most value, and some absolutely necessary for life. Could they have started anywhere other than brilliant furnaces? Fortune seekers fled the remote pine forests of northwest California a century ago, but today the mountains conceal a secret. Though they are now empty, this was the epicenter of the late 19th century California gold frenzy. From simple panning to the most advanced mining techniques, hundreds of thousands came here hoping to make a fortune. Rising to prominence with the discovery of gold valued at billions of dollars, San Francisco is among the biggest cities in the world. Though the ravenous need for gold has lessened today, the 16-1 mine is still one of the few in California still in use in the forests around Lake Tahoe. Gold mining has taken place for almost a century on the 16-1. Due to a peculiarity in the local geology, it is still among the richest gold sources worldwide. California is unique because of its position on the Pacific to North American tectonic plate boundary. The area is one large fault line with thousands of minor faults across mountain rocks. As you enter the mine, these fault lines, a network of horizontal tunnels hollowed out of the mountainside at mild gradients, are evident everywhere. They show up as a mini-fault maze separating quartz from rock. During the Jurassic period, when dinosaurs ran above the mine, hot water bubbled up and flowed through this rock carrying priceless cargo 140 million years ago. From the core of the Earth, the water carried gold that settled through the quartz seams. For the past century, miners have had to follow shimmering gold-laced quartz seams. The gold that runs through the quartz is remarkably pure, 85%. The thick tendrils of familiar yellow in the sunlight glint and glitter through the rock in the 16-1 mine. The remaining fraction is roughly 14.5% silver with traces of heavier metals. Given a 2010 price of roughly $900 per troy ounce, it is understandable why mines like this one are still in running order. One can even find basic, pure nuggets to gather from riverbeds in the area, since it is so gold-rich. Stopping to consider it, the value we attach to gold seems odd. Given its lack of value, people have gone to great lengths to obtain gold throughout history, which is odd. Copper and iron will keep you alive. Gold is useless. Most of the gold we have fought to extract has been turned into jewelry. Apart from its brilliance, gold's extreme rarity helps to explain its price. Along with all the accompanying tragedy, elation, hardship, and wealth. 3 Olympic-sized swimming pools could be filled with all the gold taken from the Earth over human history. Over human history, enough gold has been taken from the Earth to fill 3 Olympic-sized swimming pools. Gold's nearly non-existent scarcity makes it quite valuable. One of many rare elements found in even the smallest amounts on Earth, gold is so valuable because of its almost non-existent scarcity. 3 swimming pools against the scale of a planet. More than 60 elements heavier than iron abound in the universe. Some of these are valuable, gold, silver, and platinum, some of which are necessary for life, copper, and zinc, and some of which are useful, uranium, tin, and lead. Through a process known as neutron capture, very massive stars can generate trace levels of the heavier elements up to bismuth-209, element number 89, in their cores. This is known to be far from enough to explain the abundances observed today. Massive stars must abound in the universe. The conditions required to generate appreciable amounts of elements other than iron are found only in the rarest celestial events. You will miss them if you blink, since the conditions required for major concentrations of these elements will only exist for less than 2 minutes every century on average in a galaxy with 100 billion stars. Though their mass or gas content determines their lifespan and ultimate fate, all stars start from gas clouds. Stars several hundreds of times heavier than the Sun only exist for a few million years before developing into supergiants and exploding as supernovae, top row. Stars like the Sun, however, die more gently and live longer. They shine steadily for billions of years before developing into red giants and losing their outer layers as a planetary nebula in the middle row. The star's core glows for billions of years before progressively disappearing as a white dwarf. Red dwarfs, bottom, the least massive stars, fade out over tens of billions of years. Gravity causes the core of the star to collapse in on itself deep inside and then violently bounce back. The blast wave that is released produces the universe's highest temperatures. From the broken remains of the exploded star, Beetle Juice, the neutron star, will be the center of a nebula developed over millions of years. After a few million years of life, the destiny of the most famous stars on our planet is dramatic. Giant stars have used their hydrogen stores and eaten everything except iron. Hence, they are about to collapse. Nevertheless, despite their worsening state, these stars have one last violent deed: giving. It takes such great intensity that the heavy elements are feasible. Looking closely at its heart, one of these dying giants' cores finally allows gravity to take the front stage. As fusion stops and contracts at a quarter of the speed of light, this massive ball of iron falls on itself with great force. This dramatic collapse produces a sharp increase in temperature and density as the core contracts to a fraction of its starting size. Eventually, the inner core will shrink to a 30-kilometer, 19-mile diameter. By now, quantum mechanics has abruptly stopped the collapse, with densities comparable to those found inside an atomic nucleus and temperatures approaching 100 billion Kelvin. Neutrons have formed from most of the protons and electrons in the core. The Pauli exclusion principle keeps neutrons from too closely approaching each other, much as it does protons and electrons. More precisely, no 2 neutrons can be in the same quantum state. A ball of neutrons is thus 100 million times harder than a diamond, hence the most rigid substance in the universe. The superheated collapsing matter bounces back with great force when the contraction ends, since the neutrons cannot compress. As the star moves through its outer layers, its shockwave generates the highest temperatures in the universe, 100 billion degrees. Though the precise process generating this fast heating is unknown, extreme conditions rapidly form all of the heaviest elements in our universe, including gold and plutonium. A Type II supernova is the most powerful explosion known today. Since the dawn of contemporary science, we have not seen a supernova approach close by. Our galaxy's last supernova explosion was seen from Earth in 1604, a few years before the astronomical telescope was developed. Usually, one supernova erupts in the Milky Way every 100 years, but we last saw one 400 years ago. Since it's long overdue, astronomers are always searching for stars most likely to undergo supernovae. One of the main contenders is Beetle Juice, Orion's brilliant red jewel. We have been able to follow this nearby star's every movement for decades, thanks to so many telescopes pointed at it. We plotted its brightness and found it quite unstable, dimming by 15% during the past 10 years. Betelgeuse is at the top of the list of possible supernovae. Most believe Betelgeuse could explode at any moment as a supernova. Possibly only 10 million years old, this rather young star has sped through its life cycle because of its enormous size. But 10 million years is a long time to die, thus any time soon in stellar terms isn't what you might expect. Though it should go supernova sometime in the next million years, Betelgeuse could explode tomorrow. We know it will present quite a show for us when it does. The explosion will be shockingly brilliant given Betelgeuse's proximity, just 500 light-years. It might be as brilliant at night as a full moon, the most prominent star in the heavens. It will saturate the sky during the day like a second sun. The Great Orion Molecular Cloud, centered on the Orion Nebula, will be a star formation site some 1,500 years from now. NASA's Spitzer Space Telescope took this infrared picture of light from young Orion Nebula stars. Unaided sight sees the nebula as Orion's sword's hazy star. When a star's mass is more than roughly 8 times that of the Sun, it dies in a spectacular explosion. The star's outer layers propel into space at thousands of miles per hour, leaving behind a debris field of gas and dust. A tiny, dense object, known as a neutron star, frequently appears where the star once existed. Though just 16 kilometers, 10 miles across, the closely packed neutrons within it have more mass than the Sun. The brilliant blue dot in the middle of this X-ray picture of RCW 103 is believed to represent the neutron star produced when the star exploded in a supernova 2,000 years ago. In one instant, Betelgeuse will release more energy than our Sun will over its lifetime. The explosion will toss all the elements the star generated during its lifetime into space. Over millions of years, these recently produced components will distribute to create a nebula, a rich cloud of molecules floating across space. Gravity will crush the remains once a billion miles across, beyond recognition, leaving the superdense neutron core at the star's center. Betelgeuse, a hot, dense ball of matter just 30 kilometers, 19 miles across, and with the same mass as our Sun, ends as a neutron star. Though we have not seen neutron stars up close, we have seen them from afar. X-ray pictures, particularly recent images of RCW 103, the 2,000-year-old remnant of a supernova explosion occurring around 10,000 light-years away from Earth, provide vital information about these stars. See left. Betelgeuse will be quite brilliant upon explosion. It might be as brilliant at night as a full moon, the most prominent star in the heavens. During the day, it will occupy the heavens like a second sun. Though it would sound like a cosmic graveyard, the deaths of old stars birth fresh stars. This is the earthly cycle of death and rebirth manifested cosistically. Today, we can see the beautiful cycle occurring in the Orion constellation. The Sword-Handle constellation helps us to find the Orion Nebula. Seen through a telescope, the Orion Nebula is a glorious wonder of the universe, as shown by a hazy patch of light in the night sky. Hidden in its clouds are brilliant points of light. The newborn from the deaths of the old, the new stars emerging from the clouds of elements blown out by supernova explosions, and hide. A similar nebula formed our Sun 5 billion years ago. Earth was a network of planets formed from the ashes surrounding a star. Its constituents came from the nebula, a cloud of elements created by the deaths of stars drifting across space. However, the narrative goes deeper, since it is now thought that the most complex components of us, assembled in the depths of space, were not the chemical elements themselves. The origin of life. It is a piece of an asteroid. This apparently small rock fragment is older than any other rock on Earth. Thousands of meteorites crash upon Earth annually. One meteorite strikes Earth on average every month. Our solar system is home to thousands of asteroids, most of which originated in an asteroid belt formed 4,548 million years ago. Regardless of their size, asteroids are quite important, since they offer a vital understanding of the formation of the components of life. This shows that sophisticated carbon chemistry finds a home in deep space. This is quite fascinating, since it suggests that the mass of interstellar gas is starting to form the chemistry of life. Our relationship with space chemistry is closer knit. On the other side, the image shows a meteorite, a piece of rock dropped from some distance out in the solar system onto Earth. Originating from the primordial dust cloud, the nebula that collapsed 5 billion years ago to create the Sun and the planets, it is certainly older than any rock on Earth. Inside this old rock, we discovered something fascinating: amino acids, the building blocks of life, and proteins. This strongly suggests that extremely complex carbon chemistry was occurring in space, forming the building blocks of life over 4.5 billion years ago. This intriguing theory suggests that the first amino acids arrived on Earth from space by meteorites. Meteorites may have brought the fundamental elements of life to Earth from the depths of space. This amazing proof makes us rethink the slinking lights and gas and dust smudges in the sky. When we stare out into space, we can clearly see our birthplace. From the Big Bang to the present, every atom and molecule in our bodies codes the history of the universe, demonstrating our own status as children of the stars. Our story is the story of the universe. The universe combines all the elements of everyone and everything you love, hate, and cherish in the first few minutes. The stars produced it through their fiery deaths. That is, their hearts. When you die, the never-ending cycle of death and rebirth will bring those pieces back to the cosmos. What a wonderful narrative, and what an honor it is to live in such a universe. What an amazing story. One eagerly awaited celestial show is supernovae. Old stars die and create new ones. Their passing is vital for the never-ending cycle of death and rebirth that envelops our planet. Even with its grandeur, the universe is shaped by only 4 natural forces. Inside the atomic nucleus, 2 weak and strong nuclear forces remain unseen. The third force, which generates electric currents, is probably the one we are most familiar with, since we run our lives on electromagnetism. Gravity, the great sculptor, is the force working between the stars. At great distances, gravity forms the universe. Gravity formed the first stars, shaped the first planets, and arranged them into the exquisite forms of the galaxies in the formless clouds of hydrogen and helium that formerly comprised our universe. Within billions of solar systems, gravity drives the rhythms and cycles. Every planet's orbit around every star and the moons around each planet is driven by the invisible thread. Gravity keeps our feet on the ground and the universe together. Gravity serves both as a creator and a destroyer for the largest collection of matter in the universe, stars. It is relentless, not only a mild force. When the most massive stars run out of nuclear fuel, gravity crushes them out of existence. The other three forces cannot reorganize the matter in their centers to release energy and resist its inward draw. Stars spark in fleeting opposition to gravitational collapse. The least known objects of the universe come from this process. Maybe German Titov, a Soviet cosmonaut, had less ideal conditions. In 1960, the Soviet-run space program selected Yuri Gagarin and him. Out of the 20 men starting the program, only these two survived a demanding selection process that tested their mental and physical stamina to the utmost. The two fighter pilots competed fiercely during training, but only one could emerge, and Gagarin solidified his legacy. Gagarin became the first human to fly into space, following one orbit in 108 minutes on April 12, 1961. Then he came back to Earth using Vostok 1 and a parachute. Concerns about the capsule's safety during landing, especially following his spacecraft ejection at 7,000 meters, 23,000 feet, spurred Gagarin's return to Earth, a fascinating bit of space trivia. 10 minutes before he did, Vostok 1 touched down safely. Titov became the second man to orbit our planet after Gagarin returned, becoming a global celebrity and a Soviet hero. Even though Titov is still the youngest man to have traveled into space at just under 26 years old, most people will not recognize his name. On August 6, 1961, he piloted Vostok 2, making 17 Earth orbits. In addition to claiming a less glamorous place in history, Titov was the first person to experience the symptoms of a condition that has affected nearly half of people who have spent a significant amount of time in weightlessness. During the 25.3-hour mission, he was the first man to sleep in space, dozing off for a few hours while his spacecraft circled the planet. The first person to suffer from space adaptation syndrome was Titov, often referred to as space sickness. This disorder is characterized by a range of symptoms, including headaches, nausea, vomiting, and vertigo, which are typical responses to the strange feelings of space travel. Being in weightlessness is still one of the most amazing experiences an astronaut can have, but it's also one of the hardest to prepare for. Space agencies worldwide have been using the only way to create weightlessness on Earth since Titov introduced medics to space adaptation syndrome. How can we eliminate the effects of gravity? The solution is to fall toward Earth, just like Gagarin and Titov did. Project Mercury, a set of 6 manned launches that included the historic flights of John Glenn, the first American to orbit the Earth, and Alan Shepard, the first American in space on May 5, 1961, was the United States' response to the Vostok program. The Mercury 7, the astronauts chosen for the program, rose to fame in the US and eventually took to the skies. At the age of 77, John Glenn completed the Space Shuttle mission in 1998, the last flight of the Mercury 7. The television series Thunderbirds named the Tracy brothers after 5 Mercury 7 members: John, Glenn, Alan, Shepard, Gordon, Cooper, Virgil, Gus Grissom, and Scott, Carpenter. They omitted Deke Slayton and Wally Schirra. Both Deke and Wally would have been excellent Thunderbird pilots. Regrettably, we yearn for astronauts to enjoy greater recognition than rock stars. Perhaps influenced by Titov's Project Mercury training experiences, NASA devised a way to send prospective astronauts on an unprecedented journey in a standard military aircraft. NASA used a C-131 aircraft and an unusual flight path to achieve weightlessness. all of the passengers in the plane feel as though they are weightless for a brief 25-second period thanks to this parabolic path. The physiological effects are as strong as in space after 20 or 30 repetitions of this brief experience due to their weightlessness. Consequently, the C-131 earned the nickname Vomit Comet, a moniker that has persisted across all subsequent aircraft used for this mission. Due to my dedication to the space program, I have been aware of the Vomit Comet since I was young. You can only imagine how thrilled I was to learn we would ride in it for our Gravity movie. If it makes you uncomfortable, I don't care. If the Mercury 7 could handle it, so could I. This sets gravity apart from all other natural forces because it takes an additional electric charge of the opposite sign to cancel out the effect of the electric charge. When fired from a gun, the comet eliminates gravity by following a cannonball's path. A severed cable prevents the plane from falling to the ground like a lift, as it would be impossible to control. Neglecting air resistance causes the plane to accelerate toward the ground, akin to a parachute jump or a falling lift. To counteract the force of gravity, the plane must accelerate toward the ground at a rate of 9.81 meters per second squared. It also continues to fly at its typical speed to maintain aircraft control. As a result, the plane follows a parabolic trajectory. Acceleration can increase the Earth's gravitational pull, while freefall removes its effects. Only a few people are aware of the common knowledge that astronauts in space are weightless and float around inside their spacecraft. The first crucial point is that astronauts eliminate the effects of gravity by falling, not by being far from Earth. They are actually only a few hundred miles above the surface, and the strength of the Earth's gravitational field in near-Earth orbit is not all that different from the strength on the surface. Our aircraft, a modified Boeing 727-200, continues to train shuttle astronauts to this day. During the flight, I also had the opportunity to illustrate another unique, interconnected, and equally significant aspect of gravity. Isaac Newton, like Galileo many decades before him, recognized this phenomenon when he formulated his theory of gravity in 1687. The oddity is that despite gravity acting on objects proportionate to their mass, all objects fall under its force at the same rate. Newton and Galileo discovered this through experimentation, but needed to determine the cause. It is quite strange if you give it a moment's thought. Newton discovered that your mass and Earth's gravitational pull are proportionate. As a result, the force of Earth's gravity is equal to the product of your own mass and Earth's. The force between you and Earth would double if your mass doubled. It turns out that your mass totally cancels out, so everything falls at the same rate under gravity. Due to gravity, your mass also determines how fast you accelerate toward Earth. In 1971, Apollo 15 Commander Dave Scott made a famous demonstration of this peculiar phenomenon on the surface of the Moon. Scott threw a hammer and a feather to the ground and struck them simultaneously. In the high vacuum of the lunar surface, gravity is the only force acting on the falling objects. On Earth, air resistance slows the feather down, making this impossible. Regardless of your level of physics knowledge, this defies common sense and is entertaining to watch. A cannonball ought to hit the ground more quickly than an atom. It doesn't, because light falls at the same speed as a cannonball. Here's something to consider later. The key to comprehending gravity is grasping this idea. This straightforward fact was the impetus for Albert Einstein's development of general relativity, his geometric theory of gravity that remains the most accurate theoretical explanation today. Later, we will delve into Einstein's elegant theory, elucidating why everything descends at the same speed and demonstrating how falling eliminates gravity. Gravity holds the water in our oceans in place and clings to the atmosphere near the Earth. It's what causes the rain and rivers to flow, drives the global weather and ocean currents, causes volcanoes to erupt, and causes earthquakes to split the Earth. On a larger scale, though, gravity also matters. Gravity is the powerful sculptor who brought order out of chaos in the universe, from the tiniest dust particle to the largest star. Gravity is the force that governs everything in the universe. Gravity is the invisible thread that directs everything from the artificial satellites that orbit our planet, forming the technological infrastructure of the 21st century, to the Moon, our only natural satellite, which circles the planet every 27.3 days. From our planet's 365-day orbit around the Sun to the orbits of the 7 planets and 166 known moons in our neighborhood, gravity drives the motion of every planet, moon, ball of rock, and mote of dust in our solar system. No matter how small or large, the gravitational pull of everything still conducts the universe's flow outside of our solar system. The Milky Way galaxy, which revolves around our solar system, is dominated by a supermassive black hole at the center of a whirling system of more than 200 billion gravitationally bound stars. Gravity guides the galaxies through the vast universe, making even this enormous, rotating structure different from the end of the universe's cycle. The Virgo supercluster of galaxies is an excellent illustration of the effects of gravitational pull. This cluster gravitationally pulls the local group of galaxies surrounding our Milky Way galaxy. A whirlpool system of more than 200 billion gravitationally bound stars revolves around Sagittarius A, the supermassive black hole at the center of the Milky Way galaxy. The Virgo cluster's center is the elliptical galaxy M87. This huge galaxy is home to a family of 15,000 globular star clusters, several trillion stars, and a black hole possibly gravitationally drawn from adjacent dwarf galaxies. Beyond our solar system, gravity still controls the universe's flow, influencing everything, big or small. American astronomer Edwin Hubble designated the collection of more than 30 galaxies, including our galaxy, the Local Group, in 1936. Covering more than 10 million light-years, this massive dumbbell-shaped construction is home to billions and billions of stars, including the trillion stars that make up Andromeda, our big galactic neighbor. Like the Moon orbiting Earth, Earth orbits the Sun, and the Sun orbits the Milky Way. The Local Group revolves around its common center of gravity, located some 2.5 million light-years apart between the two most massive galaxies in the group, Andromeda and our Milky Way. Still, this enormous population of galaxies is not even the biggest known gravitationally bound structure. Reading this book will take you on an amazing trip through gravity. We participate in a more expansive, gravitationally driven cycle than merely whirling around Earth. Earth revolves once a day on its axis, orbiting the Sun at just over 100,000 kilometers, 62,137 miles per hour, rotating around the center of our galaxy at 220 kilometers, 136 miles per second, and the whole Milky Way tearing around the center of gravity at 600 kilometers, 372 miles per second. The Local Group is part of the gravitationally bound family of at least 100 galaxy clusters known as the Virgo supercluster. Though only one of the millions of superclusters in the observable universe, the Virgo supercluster is vast, spanning more than 110 million light-years, and nobody knows how long it will take our Local Group to pass around it. Experts say that even superclusters are parts of much bigger structures known as galaxy filaments or massive walls kept together by gravity. We belong to the Pisces-Cetus supercluster complex. Gravity has had an unbounded influence over the universe's history at all distance scales. Surprisingly, given its great scope and universal relevance, it is the first force humans completely understand. Curiosity-driven science is the pillar of our civilization, as shown by the numerous cases of chance and serendipity leading to the biggest scientific discoveries in history. One of the most well-known is the convoluted story of Newton's evolution of his theory of gravity, the first basic universal law of physics. The most lethal and last significant bubonic plague epidemic to strike England was the Great Plague of 1665. The disease contracted from rodents claimed over 100,000 lives. London was the epidemic's epicenter, but because of the network of ties between the capital and the rest of the country, the illness quickly swept over England. They employed extreme and often useless techniques to stop the disease from spreading and begin fires to clean the air, including culling helpless dogs and cats. They closed schools and quarantined sick towns. One impacted site was Trinity College, Cambridge, where Isaac Newton missed summer break in 1665. At 22, Newton returned to his family's Woolsthorpe, Lincolnshire, house after graduating from Cambridge, beset with plague. Reading many books on Euclid and Descartes' geometry piqued his curiosity in mathematics. Later, he wrote on a book he had bought at a fair on astronomy. Though a poor student, his forced absence allowed him time to think. His obsession with the physical world and the laws controlling it began to take shape. Over the next 2 years, his private studies set the foundation for most of his later work in several disciplines, including gravity, calculus, and optics. When he returned to Cambridge in 1667, the university voted him a fellow. Previously held by Stephen Hawking, he was appointed the Lucasian Professor of Mathematics in October 1670. Currently held by string theorist Michael Green, who is still working on the nature of gravity problems. Newton worked on several scientific and pseudo-scientific projects for the next 20 years, including alchemy and apocalyptic date predictions, and lectured. Published in 1687, Newton's Philosophiae Naturalis Principia Mathematica, also known as the Principia, describes the force of gravity guiding the Apollo astronauts on their lunar trip. Its simplicity, applicability, and effects on scientific philosophy are lovely. Of Newton, the economist John Maynard Keynes remarked that he was the last of the magicians rather than the first in the age of reason. Though this is untrue, what can one expect from an economist? In a vacuum, the feather and ball fall at the same speed, showing that objects of different masses accelerate at the same rates at the same gravitational potential. A vacuum does not have air resistance. Hence, we cannot see this phenomenon on Earth. By dropping a feather and a hammer on the moon, devoid of atmosphere, and tracking their consistent fall rate, an Apollo astronaut confirmed the validity of this principle. This time-lapse picture deftly shows the idea of gravity. Newton's law of universal gravitation has a mathematical form. The force, F, between two objects, is thus the product of their masses, m1 and m2, divided by the square of their distance. Newton's law of universal gravitation is lovely, for numerous reasons. It is universal. Thus, it affects everything, not in the vicinity of black holes, too near to massive stars, or moving near the speed of light. In these situations, one needs Einstein's more exact general relativity theory. It is sufficiently accurate for planetary orbits around stars, stars around galaxies, and galaxy movements. It also pertains to the universe's past outside the first moments following the Big Bang. We should not take this for granted, since the derivation of the law came from the work of Tycho Brahe and Johannes Kepler, who concentrated just on the motion of the planets around the Sun. It is fascinating and significant, since a law controlling the motion of the galaxies is the same one controlling the clockwork of our solar system. According to this view, Newton's law of gravitation is the first example of a universal law, since the same laws of physics control our world. Modern basic science is built on one elegant and beautiful mathematical formula that captures the complicated motion of everything in the cosmos. Newton's simple equation lets you find the positions of the planets and moons in the solar system at any one moment in the future. This holds true for all solar systems in the universe. Consequently, you do not have to spend every night sitting down with a telescope and applying trial and error to ascertain the planetary and moon positions in the solar system. With a mass of almost 6 million kg, the force between us and our planet is strong enough to ground us. On the scale of planets, however, gravity can sculpt and shape their surfaces in profoundly unexpected ways, not only keeping objects on the ground and in orbit. From the microscopic, undetectable force of attraction between two rocks on the ground to the greater force we are now experiencing between our bodies and the great rock upon which we're standing, Newton found that all objects are subject to gravitational attraction. Rising almost 9 kilometers, 5.5 miles, Mount Everest is the highest mountain above sea level. It towers above all else on Earth, but perched shockingly on the surface of a far smaller planet, the highest mountain in the solar system dwarfs Everest. Mars is like our planet in many respects, around 78 million kilometers, 48 million miles, from Earth. Water once flowed from the mountains to the seas, scarring its surface and dissipating its gravitational potential energy as it dropped. But today, the water has left Mars. However, Mars was unable to retain its atmosphere despite being further from the Sun because its gravitational pull is much less than Earth, since Mars is just around 10% as massive. Along with its atmosphere, the prospect of liquid water flowing on the Martian surface disappeared, leaving the red planet geologically dead and arid. But Mars's mountains expose a surprising result from its reduced surface gravity. Rising to roughly 24 kilometers, 15 miles, Olympus Mons, an extinct volcano, rules the solar system at almost exactly the height of 3 Mount Everests stacked atop one another. Though there is a basic limit to the height of mountains on any given planet, the fact that a smaller planet has higher mountains is not a coincidence. It is rather due in part to environmental factors like the rate of erosion and the specifics of the planet's geological past. Using Newton's equation, a simple computation reveals that the gravitational pull at Mars's surface is roughly 40% stronger than ours, altering the weight of everything since Mars's radius is roughly half that of Earth and its mass is only 10%. According to the theory of special relativity, an object's mass is an invariant quantity. That is, everyone in the universe measures the same value independent of location or motion. Though we don't usually consider it on Earth, mass and weight differ. An object's mass defines its material content and is a constant independent of its location in the universe. If you think about how you would weigh yourself, weight is different. We measure it in units of force, newtons, rather than kg, which is straightforward if you press down on the bathroom scales. The higher the weight reading is, the harder you push. The strength of Earth's gravity dictates the force you apply on the scales. Should I have raised the Vomit Comet scales and attempted to stand on them, I would have been suspended above them, and hence their weight would have been 0. Mars has 40% of Earth's gravitational pull. Thus, the great Olympus Mons can exist there, but if it were transported to Earth, its great weight would cause it to sink into the ground. Thus, your weight is determined by the planet's mass and yourself. Another instance of the equivalency principle is the weight change under acceleration. Consequently, Olympus Mons would weigh roughly 2.5 times Mars and eclipse all other mountains if placed on Earth. A planet our size could not support a mountain like Olympus Mons. It would weigh too much. Rising gradually more than 1 kilometer, half a mile, above Everest from its base, Mauna Kea is the largest dormant volcano in Hawaii. Mauna Kea's absolute limit is set by our gravity, thus as high as a mountain. The idea of weight can be complicated. We have already covered the deviations from the general rule, which states that your weight on Earth equals 9.81 times your mass. One issue is that every point on Earth's surface experiences somewhat different gravitational strength. The most obvious difference is elevation. I would weigh less on the brink of the Fish River Canyon than I would if I were standing on the canyon floor. I'm farther from the center of Earth at the top of the canyon than at the bottom. Thus, gravity is lower. Earth's density also varies. Some areas of its surface and subsurface have more massive materials than others, which affects the local gravitational field. Complicating matters even more is the Earth's spinning, which causes you to accelerate on its surface. The equivalency principle allows this acceleration to alter the gravity's strength you experience. As you approach the equator, this acceleration gets faster, lowering the gravitational acceleration experienced there. Because spinning reduces gravity, Earth bulges at the equator. The result is that at the north and south poles, you weigh roughly 0.5% less than at the equator. Scientists have precisely calculated how Earth's gravitational field varies with changing crust density and surface feature presence. To show the outcomes, they subsequently drew a map called the GeoID. On Earth, Olympus Mons weighs roughly 2.5 times as much as it does on Mars. A mountain this scale would be too weighty for a planet the size of ours. The strength of the surface gravity of any given planet determines a basic limit to the height of mountains on that planet. With Mars's gravitational pull at its surface, roughly 40% of that on Earth, the extinct volcano Olympus Mons dominates every other mountain in the solar system, almost as tall as 3 Mount Everests piled on top of one another. Furthermore, it is not a coincidence that a smaller planet boasts more mountains, partly due to geological and environmental aspects. Launched in March 2009, the GOSI-E satellite of the European Space Agency captured images of the nuclear field of Earth. 3 ultra-sensitive accelerometers on GOSI respond to minute changes in Earth's gravitational strength as the satellite circles. GOSI spent 2 months gathering the data to generate this amazing picture, the first accurate global mapping of the strength of gravity, skimming the edge of Earth's atmosphere at 250 kilometers, 155 miles. The surface of the Earth is laid under by the rock's density. On Earth, features like mountains and ocean trenches cause these fluctuations. Hence, we show the image as an equipotential surface. This implies that the picture would match the water height everywhere if one ocean covered the whole Earth. This map amply illustrates Iceland's stronger gravitational field than England. But even if we did not notice these variations, I would weigh less in Manchester than in Reykjavik at the same elevation. Naturally, as this data is a high-precision geological tool, the unmatched degree of detail will enable a better knowledge of how our planet works. The map shows the baseline water surface free of tides, winds, and currents, benefiting oceanographers. It is imperative to know the elements driving water movement across the seas of our planet. Accurate climate models depend on accurate predictions of energy transfer around our planet. Therefore, the planet's surface offers a great deal of comprehensive knowledge about its structure by indicating its gravity's strength. Regarding the true height of the ocean surface, the Moon is the most crucial element, but it is also invisible. This picture, taken in May 2010 by a NASA satellite, shows the eruption of Eyjafjallajökull, an Icelandic volcano. The GeoID clarifies invisible structures on our planet, such as here in Iceland, where magma is welling upward from the Earth's mantle, influencing the planet's gravitational field. Although many of the planets in our solar system feature families of moons, such as Jupiter's 63 and Neptune's 13, our planet has one moon. Mars only has one moon, unlike Neptune, which boasts 2 small satellites. For almost 4.5 billion years, this moon has been our steady friend as we have crossed the cosmos. None else in our solar system has a parent planet with a moon as big as ours, a quarter of its diameter, orbiting only 380,000 kilometers, 236,000 miles from Earth. Though its parent planets, Jupiter and Saturn, are greatly larger than Earth, the Moon ranks fifth largest in the solar system after Titan, Ganymede, Callisto, and Io. This brings the Moon and Earth close to a binary planet arrangement. According to the present best theory on the formation of our Moon, a Mars-sized planet called Theia collided with the recently formed Earth about 4.5 billion years ago, hurling rock into orbit and gradually condensing into the lunar framework we know today. Though Earth is much less dense because of its smaller iron core, the Moon's composition resembles Earth's outer crust. This would be predicted by a glancing blow from the Theia-Earth collision, which left Earth's iron core intact, and Earth's relative iron content in the Moon changed. This suggests that the Moon's gravitational field is far stronger than ours. Neil Armstrong weighed just 26 kilo, 58 pounds, although donning a spacesuit weighing 81 kilos, 180 pounds, on Earth when he set foot on the Moon. About 1/6 of Earth's gravitational field exists in the Moon. The Moon still significantly influences Earth despite its rather weak gravitational attraction. The Moon obviously affects our sea level. The Earth's and the Moon's gravitational pull squashes everything and generates tides. Because of its closeness to Earth, the Moon's gravitational pull differs greatly on one side of the planet from another. Subtracting Earth's gravitational field, the image, right, shows the net gravitational force the Moon generates at every point on Earth, as seen by someone seated at Earth's center. As one would expect, what is left is a net gravitational force dragging the side of the Earth facing the Moon toward the Moon. Still, a net force is dragging the other side of Earth away from the Moon. Furthermore, the lunar gravity adds to the Earth's gravitational pull and squashes everything at right angles to the Moon's position. The tides originate from water. Since water is more easily stretched than the rock forming the ocean floor, the ocean's water bulges outward, moving the ground beneath the Moon and on the other side of Earth. Although the water heights vary just a few meters, the shoreline's form will greatly affect this difference. It's crucial to underline that tides also occur on Earth's surface rocks, proving that gravity influences more than only the water on the planet. Still, rocks are rather flexible. Thus, they don't stretch noticeably. Still, tidal influences cause the surface of the Earth to rise and drop a few centimeters. Two high and low tides daily arise from Earth, rotating beneath the raised tidal bulge in the oceans, sweeping the distorted water surface past the coastlines. Gravity is always reciprocal. Thus, the Earth must produce the tides that sweep across the surface of the Moon, as the Moon does on Earth. The Moon's gravity has shifted our planet's position and that of its neighbor. The Earth and the Moon have a reciprocal relationship. Half of the Moon's surface has stayed hidden from us throughout human history. We only learned of this hidden terrain in 1959, when the Soviet Lunar 3 probe snapped the first images of the Moon's far side. 9 years later, the Apollo 8 astronauts became the first people to depart Earth's orbit and view the far side of the Moon close by. The Moon's gravitational influences cause only one side to face Earth, giving the apparently limitless night sky a stationary and frozen-in-time quality. From Earth billions of years ago, when the Moon was a child, it rotated much more rapidly when both sides of its surface were visible from Earth, and when it was born, our satellite would have looked quite different. Earth's gravity pulled the Moon from birth, which would have been stronger than it is now since the Moon was nearer Earth. Two equal-sized tidal bulges explain why two daily high waters are produced. The main force driving the tides is the lunar gravity differential field at the Earth's surface. The Moon gradually separates from Earth as the Earth-Moon system gets near-perfect tidal locking. An amazing feat of planetary heavy lifting may have distorted the Moon's crust by up to 7 meters 2 moons. Newton's law of universal gravitation shows that gravity is a reciprocal relationship. Earth must thus create tides on the surface of the moon, just as the moon creates tides on Earth. Naturally, not water, but the solid rock on the surface of the moon creates these tides. Although the tide's rise wasn't instantaneous, the intriguing effect of this massive tidal bulge sweeping across the moon's surface was that the rocking tide dragged across the moon's giant parent planet, hanging in the lunar sky. But the tide's timing wasn't the moon's surface to react to the moon's Earth's pull. The moon's modest rotation during that period will cause the tide to be ahead of Earth's due rather than exactly aligned. Under Earth's sweeping motion, tidal locking occurs when the tidal bulge stays exactly where it is on the surface of the moon. This locking progressively brings the moon's rotation speed into line with its orbit. Stated differently, Earth's gravity serves as a giant brake, guiding the misshapen planet back into harmony. The Earth-Moon system is still developing toward perfect tidal locking, and one fascinating result is that the Moon is progressively moving away from Earth at just under 4 centimeters, 1.5 inches, annually. Currently almost, but not quite tidally locked to Earth, the Moon takes 1 month to rotate around its axis and 1 month to orbit Earth. Thus, the Moon has no dark side. The side we cannot see gets plenty of sunlight. Beyond forming planets and moons and spanning empty space, gravity can produce whole new worlds. This process is seen daily and nightly in the sky. Third party. This one is among the most odd lights in our night sky. Those who have seen its radiance have been confused for millennia since they thought a fresh day was just around the corner. Referring to it as the false dawn, the Prophet Muhammad advised Muslims not to mistake it for the actual dawn when deciding when to pray daily. Not connected to the coming or going of our star, this enchanted radiance that shows on the horizon just before sunrise and after sunset is a spectral reminder of the beginning of our world and the power of gravity. A weak, whitish glow, the zodiacal light, appears to rise from the horizon like a triangle. Italian astronomer Giovanni Cassini first looked at this unusual occurrence in 1683. The ethereal light perplexed many scientists of the day, usually ascribed as coming from the sun's atmosphere since it rose above the horizon before the sun itself. Nicolas Fatio de Duillier, one of Cassini's pupils, finally revealed its source and gave a first glance at how the planets and moons in our solar system evolved. The zodiacal light originated 5 billion years ago at the dawn of our solar system. Back then, the basis of everything we lived with was just a cloud of gas and dust. The sun, planets, or moons were absent. Our whole solar system floats across space as a huge asymmetrical cloud. It is thought that the explosion shockwave of a nearby star caused minute fluctuations in the density of the cloud. It also caused rotation. The denser areas started to grow due to a small increase in gravitational pull. The sun emerged as the biggest. Early in the solar system, there would have been no planets. Instead, a protoplanetary disk, a spinning disk of matter, surrounded the sun. Large objects, the size of small asteroids, planetesimals, would have been created by accident as the disk's microscopic dust particles collided and clumped over time. Once the bigger planetesimals were big enough to clearly have a gravitational pull, their growth quickened as they swept up the matter close by. About 100 million years later, the biggest planetesimals turned into the modern planets and moons. Not all of the stuff from the original cloud evolved into planets or moons. Beyond Mars, the solar system should have another planet, but a gravitational pull between Jupiter and the Sun keeps this planet from developing. Comprising dust and trash, the asteroid belt substitutes for a 9th planet. The false dawn results from dust generated by collisions inside the asteroid belt, since the belt is generally too far away. and the asteroids are too small to be seen with the unaided eye from Earth. Sunlight, reflecting off the rubble of a failed planet, a relic of the early solar system, causes the faint glow of the zodiacal light after sunset and before sunrise as a lovely, shimmering reminder of our beginnings. Scientists have long argued about the white, hazy glow on the horizon just before sunrise and after sunset. This so-called zodiacal light is waste left over from solar system gravitational tug-of-war-induced asteroid belt collisions. Although the asteroid belt is usually too far away, and the asteroids are too small for the unaided eye to view from Earth, the dust generated by collisions within the belt gives the false dawn its look. Beyond Mars, another planet ought to have developed from the primordial dust in the solar system, but the Sun's opposing gravitational pull stops this, leaving behind an asteroid belt of dust and trash. As we have covered, stars and planets are produced by the gravitational collapse of dust clouds. Two interpretations of this phenomenon are either the force of gravity pulls everything together, or the small particles in the primordial dust cloud floating around in each other's tiny gravitational fields have gravitational potential energy. Like the raindrops descending high in the mountains above Fish River Canyon, these particles would all try to fall downhill to lower their gravitational potential energy. This results in a basic and deep physics principle explaining everything in the universe. If an entity can lower its potential energy, it will try to do so. What causes a ball to roll down a hill? You could explain that the ball rolls down because its gravitational potential energy is lower at the bottom than at the top. The ball is pulled down the hill by a force. Since the terms are interchangeable, physicists often deal with energies rather than forces. Some theories claim the blue marble picture might be human history's most often shared image. Stars and planets are spherical because a sphere guarantees that everything is as near to the center as possible. The shape that minimizes the gravitational potential energy will be the one that finally forms in a collapsing dust cloud, since anything further from the center of the cloud will absorb more gravitational potential energy. Astronomer Carl Jansky found in the 1930s that radio waves could be detected in addition to the visible portion of the electromagnetic spectrum, which allowed for the exploration of the cosmos. Jansky recorded the radio waves from the sky over months, using an antenna resembling a Meccano set more than the VLA. At first, he distinguished between two kinds of signals: radio waves produced by thunderstorms close by, and radio waves produced by thunderstorms farther away. He also discovered a third type, which he believed to be static. The fascinating thing about the static was that it seemed to rise and fall every day, which is why Jansky thought it was caused by radio waves from the sun. But after a few weeks, the static's rise and fall started to stray from a 24-hour pattern. Jansky could follow the enigmatic signal by rotating his antennae on a set of Ford Model T tires. He quickly discovered that the brightest point was coming from the Milky Way galaxy's center, toward the constellation of Sagittarius rather than the Sun. Jansky's pioneering work did not immediately lead to the expansion of the new field of radio astronomy, which coincided with the consequences of the Great Depression on the economy. Nevertheless, radio sky exploration has become one of the most successful means of understanding the universe outside our solar system. Recent NASA Spitzer Space Telescope observations show that Andromeda, the closest spiral galaxy to the Milky Way galaxy and the furthest object seen with the unaided eye when looking up at the night sky, may be home to 1 trillion suns, even if it would only seem like a smudge in the sky out of the roughly 6,000 stars visible from Earth. Though only 100 billion galaxies are in the observable universe, Andromeda stands out for one reason. As the universe expands, most galaxies speed away from one another, but Andromeda is headed straight for us, approaching at a rate of roughly 500,000 kilometers, 310,000 miles. Gravity guides the two galaxies to finally meet. Galactic collisions and the resultant mergers of galaxies are not unusual events in the history of the universe. Over the billions of years they have lived, both the Milky Way and Andromeda galaxies have absorbed other galaxies into their structures. This may sound like a rare and catastrophic event, the meeting of 1 trillion suns. From this angle, Andromeda looks slanted. In the series of images on the following page, we modeled a galactic collision between our Milky Way galaxy and Andromeda, our neighbor, from the bottom to the left of Andromeda, then to the upper right. After the first collision, both the Milky Way and Andromeda show an open spiral pattern, complete with long tidal tails and the development of a connecting bridge of stars. The galaxies first separate, but they finally reconverge and collide once more. The time scale between each sequence frame is 90 million years. The images span 1 million light-years. The enormous organizational force of nature is a mystery, despite its influence and reach. It is the weakest force in the universe and a pervasive influence. We overcome it every day through routine actions because it's so weak. The force of gravity on the entire planet tries to stop you when you lift up a teacup, but your arm's strength wins. We don't know why this weakness exists, but the answer becomes obvious when we think about what happens when you raise the cup. Electromagnetism is the force that keeps your body's atoms together and drives your muscles. You will always prevail in a conflict with Earth because it is a million times more powerful than gravity. However, evolution does not create animals with stronger muscles and skeletons than are necessary, and we have evolved to live on the surface of a planet with a specific gravitational field strength. Biology rarely wastes valuable resources. Someone at the BBC decided it would be amusing to show how a human body, mine included, would react if transported to a larger planet to illustrate this. Newton's law of gravitation states that Neptune's surface gravity is only roughly 14% higher than Earth's, or 1.14 g, because its radius is 3.89 times that of Earth at the equator. As I raised my arms, which were 14% heavier than usual, I could already feel the difference, even with such a small change. Having flown in both a Lightning and a Hunter, I agree that the centrifuge is far more intense than anything you would experience in a fighter jet. It has to do with the sustained G-force. I spoke with an F-16 pilot who had experienced fast acceleration and deceleration up to 9G. NATO requirements state that all fighter pilots must be able to handle this rough ride without fainting. You find oddity in that our bodies have not evolved to resist the weak force of gravity at magnitudes much above those of Earth. With a mass 333,000 times that of our planet, the Sun is the body in the solar system with the strongest surface gravitational force. Its surface gravity is more than 28 times stronger. That speed would cause an unsurvivable G-load, so the centrifuge cannot run. Our next stop is an alien-populated planet among the most unusual in the universe. We must search for more exotic objects than stars and venture outside our solar system to find stronger gravitational fields. Gas and dust spiral into the black hole, releasing much radiation, more than a galaxy with 1 trillion suns could produce. Quasars are the brightest, strongest, and most energetic objects in the universe. Postgraduate student Jocelyn Bell and her supervisor Anthony Hewish searched for them using a recently built radio telescope at Cambridge. It is now commonly accepted that the small, compact areas surrounding supermassive black holes at the core of very young galaxies are universes or quasi-stellar radio sources. Searching the data for these very active, ancient galactic centers, Bell and Hewish came upon an unusual signal, a precisely repeated pulse every 1.3373 seconds. The Cambridge team dubbed this signal LGM-1, or Little Green Men, since they found it difficult to believe that such a fast, consistent pulse could arise naturally. Researchers have discovered a small, ordinary-looking painting among the rocks at Chaco Canyon, depicting the explosion of the star responsible for the Crab Nebula. Amazingly, Bell and Hewish were not the first to see one of these wonders. An ancient civilization had seen the birth of one almost 1,000 years earlier. A radio beacon from an extraterrestrial civilization would have alerted you. When astronomer Sir Fred Hoyle heard the announcement, he realized instantly that the source was natural. But in 1974, Hewish and fellow astronomer Martin Ryle, though confusingly and controversially not Bell, were awarded the Nobel Prize in Physics for their new discovery. Along the floor of the dry Chaco Canyon in New Mexico, a massive civilization constructed enormous stone buildings known as the Great Houses a millennium ago, between AD 900 and 1150. Until the 19th century, these structures were the biggest artificial constructions in North America. More than 700 rooms are in the largest of these structures. Many are still standing. Oddly, no signs of cooking utensils, fires, or animal bones suggest that these structures were not habitations. Instead, they seem to have been largely ceremonial. Some archaeologists believe that the canyon's design, including its complex and precisely oriented road system, symbolically reaffirms the canyon's position as the center of the universe, as well as the center of local culture, commerce, and religion. The roads and structures in the canyon and its environs align with the compass points and significant times in the sun's annual cycle, like the summer and winter solstices. Although it is difficult to determine whether all of the claimed alignments were deliberate, it is known that the Chacoan peoples had a highly developed cosmology, including creation stories for the constellations and the universe, and were keen observers of the skies. We arrived at a hidden spot a mile away from the main ruins. Since I was a young boy, I have been aware of it and have longed to visit. I was unaware of the location of Chaco Canyon, but I was conscious that a small, unremarkable painting on the underside of a rocky overhang next to a dry riverbed half a world away existed. I first learned about the wonders of the cosmos from Carl Sagan's Cosmos, both the book and the television show. In The Lives of the Stars, a tiny black and white image of the painting depicts three symbols: a bright star, a crescent moon, and a handprint. The painting was created around AD 1054, one of history's most spectacular astronomical events. A nearby star burst on July 4th, AD 1054. Since the explosion was visible during the day for 3 weeks and the fading new star was still visible at night for 2 years, the Chacons would have also witnessed the explosion, which Chinese astronomers documented on the precise date. We will never know, but it would have ruled the skies, a strange and magical sight feared or celebrated. The Crab Nebula, one of the most well-known and exquisite sights in the sky today, is a remnant of the explosion, so we know exactly where it occurred. From the remains of the great houses of Chaco Canyon and the breathtaking rock faces that surround the floor of this dry valley, the Crab Nebula is best seen every 18.5 years. Unexpectedly, physicists Andrew Leonard and Freeman Dyson demonstrated in 1967 that normal matter cannot collapse due to a quantum mechanical effect known as the Pauli exclusion principle. Nature classifies particles into 2 categories based on a characteristic known as spin. Fermion is the collective term for the half-integer spin of fundamental matter particles like electrons and quarks, and composite particles like protons and neutrons. Bosons are the fundamental force-carrying particles with an integer spin, like photons. The crucial characteristic of fermions is that no two can occupy the same quantum state. To put it more precisely, only a few fermions can occupy a single spot. This clarifies the chemistry process and the stability of atoms. Around the atomic nucleus, electrons occupy different shells. As the number of electrons increases, they move into orbits farther from the nucleus. The actions of an element's outermost electrons solely determine its chemical characteristics. If the exclusion principle didn't exist, all electrons would cram into the lowest orbit, leading to no complex chemical reactions or people. About 6,000 light-years distant from Earth, NASA's Hubble Space Telescope photographed the Crab Nebula, the leftovers of a star that exploded as a supernova in AD 1054 with hitherto unheard-of clarity on the nebula's core. The fast-expanding remnant of a star once roughly 10 times as massive as our Sun, the Crab Nebula is 11 light-years across and growing at 1,500 kilometers per second. For masses greater than this, gravity prevents the electrons from moving closer to one another. Rather, they surrender and vanish. What would happen if we created more massive white dwarfs, thereby increasing the gravitational force? The renowned Indian astrophysicist Subrahmanyan Chandrase. Considered a constantly expanding gas cloud, this composite picture superimposes the Crab Nebula's optical, red, and X-ray, blue, images. It is most famously recognizable. Astronomers using the Parkes Radio Telescope in Australia and the Hubble Telescope at the Jodrell Bank Centre for Astrophysics near Manchester announced in January 2004 that they had discovered a double pulsar system, undoubtedly one of the universe's most amazing wonders. The system comprises two pulsars that orbit one another every 2.4 hours. One pulsar has a rotational period of 23 thousandths of a second, while the other has a period of 2.8 seconds. The entire system could easily fit inside our Sun due to the orbit's tiny diameter. Because pulsars are such precise clocks, astronomers can test Einstein's theory of gravity under the most extreme circumstances possible. Imagine how space and time would be severely bent and warped near these two enormous, rotating neutron stars. In what is arguably the most potent and exquisite test of any physical theory I am aware of, the double pulsar system has verified the predictions of Einstein's theory of general relativity, our best current theory of gravity, with an accuracy of better than 0.05%. How magnificent, strong, and amazing is the human mind, that a man at the turn of the 20th century could come up with a theory of gravity that can so accurately explain the motion of the most strange objects in the universe under the most extreme known circumstances, motivated by careful consideration of falling rocks and elevators. I adore physics because of this. Newton's law of universal gravitation transformed our understanding of the universe in 1687. Planets orbit the Sun, solar systems orbit galaxies, and galaxies orbit one another. However, Newton's law is only a gravity model. It does not explain the nature of gravity or the fundamental conundrum of why all objects fall in gravitational fields at the same speed. By going over Newton's well-known equation once more, we can rephrase this query. Consider another of Newton's equations. Newton's second law of motion explains the stone's acceleration in response to an applied force. It states that the force equals the stone's acceleration, a. Assuming m1 is the mass of the Earth and m2 is the mass of a stone falling towards Earth, this asserts that the gravitational force between two objects is proportional to the product of their masses. We can thus mathematically rewrite F on May as a me or Fm. Einstein would have known Newton's theory had problems beyond philosophy, even without being motivated. Of these, the most unsettling was the obviously problematic behavior of a rock ball more than 77 million kilometers, 48 million miles away from Earth. For thousands of years, people have been fascinated by the planet Mercury. Mercury, the planet closest to the Sun, endures the most severe temperature fluctuations in the solar system. Mercury is a challenging planet to view from Earth because of its closeness to our star. But sometimes the planets line up so that Mercury crosses the Sun's face directly. These Mercury transits, which only happen 13 or 14 times every century, are among the most spectacular astronomical events. Mercury has the most erratic orbit out of all the solar system planets. Mercury is only 46 million kilometers, 28 million miles from the Sun at its closest point, and more than 69 million kilometers, 42 million miles, away at its furthest point. Mercury's highly elliptical orbit causes its movement speed to vary greatly throughout its orbit, making high-precision measurements necessary for mapping and forecasting its upcoming transits. Scientists worldwide would assemble to observe Mercury's infrequent transits during the 17th and 18th centuries. These scientists could predict exactly when and where they could see the spectacle by using Newton's law of gravity. But when Mercury repeatedly failed to show up on time, it became a source of scientific fascination and embarrassment. The planet frequently passed through the Sun's disk several hours later than anticipated. For decades, astronomers have searched for Vulcan but have not located it since it does not exist. The mistakes in the forecasts point to a more fundamental problem. A modification to Newton's theory of universal gravitation is required.